Hey everybody, let's see, it's gonna start the stream on me here. Is it gonna start? Are we doing it? We'll see if you can see me. Let me see if it's loaded in. Yep, we're loaded in there. There we go. Yeah, can you see this? No, it's that. Yeah, no, you can see it. It's on my screen there. The whole thing just crashed. So like literally it just crashed, which I've never had happen. It's just crazy to me. There's edit in paint, just the whole stream just crashed. So it just went blank and I was like, well, there we go. Are we still in the Kahoot? Are people still in? Are you still in the Kahoot, yes or no? We will have to put up another link to this. You're still in? Good, good, good. Okay. Woo! Okay. Okay, we're all still in. Good deal. Thank you so much. Hopefully we got a bunch of people still here. Man, this is the craziest. I was going to show how to get expected cell count, and then we just crashed. My screen went black. The monitors like reset, and I was like, I've never had a stream crash like that. So there we go. Review 3 in the chat. We got to re-wake up Mubot. Okay, let's get started here. Expected cell count is row total times column total over, this is normal. Mubot sometimes crashes the universe. That is a normal black screen right there. Row total times column total over grand total. Row total times column total over grand total. Go ahead and type that in the chat right now just for practice. Expected cell counts, which you may have to find later on in this review. Row total times column total over grand total. Put it in the chat right now. Let's throw you some points. Mubot is back awake. So row total times column total over grand total finds the expected cell count. And I have a calculator out next to you because there's going to be some formulas coming up here soon. Mubot is back awake. Here we go. Let's get started with that next question. Let's do this. Let's not crash anymore. I'm working on waking up at 3 a.m. and I'm tired, but we're not going to crash. Which of the following must be met for the chi-squared test of independence? There could be more than one right answer right here. There could be more than one. Oh man, you guys can hear the audio now? You guys can. Testing 1, 2. Testing. Yes. Oh, it's coming through my audio too. Coming through the Go XLR and this. You hear the music? Good. Take this one all the way down. Yep, it's coming through my audio. I was like, I just can't hear the music. Really sad. It's been all semester? Have only I been able to hear the music? So with these right here, nearly normal is for what kind of data? And take notes if you don't have these. Nearly normal is for what kind of data? Don't worry if you got it wrong, but nearly normal is for what kind of data? Nearly normal is for what kind of data? Put it in the chat. Show me you know it. Nearly normal is for, it can be for the 2 sample t, it's for all the t's, for all the quantitative. Nearly normal is for quantitative variables. Success failure is for categorical, just one categorical variable. Where expected cell count is we have to have at least 5 expected cell counts via the row total times column total over grand total formula. You can just take the smallest one if you want, because if it's large enough, all the other ones are large enough. And count data is when we have a 2 categorical variable combination, kind of like CC, but not QQ. So we have these conditions right here. Let's do the next question. Here we go with the leaderboard. Kind llama. Where'd the bunny go? Elated piranha, radiant cheetah looking like a Einstein world, fuzzy dove, and diligent panther. Next question. The chi-squared test statistic is found how? How do we get the chi-squared test statistic, which is this one right here? That might look like a p-value. Why? Why does that kind of look like a p-value to you? Does anyone have any idea why that chi-squared test statistic, the Pearson chi-squared test statistic, why does it kind of look like a p-value? Why does it kind of look like a p-value? Oh no! Don't worry if you get it wrong. Why does it kind of look like a p-value? You could mistake that for a p-value right there. Not a p-value though. P-values are probabilities. And because they're probabilities, p-values have to be between what and what? P-values have to be between what and what? P-value would have to be between what and what? P-values have to be between 0 and 1. Great job, Lillian and Savannah right there. No worries, Mally. Exactly. P-values have to be between 1 and 0. And so we go to the chi-squared applet right here. And what we'd want to do is we'd want to find a p-value using a chi-squared. And you could enter in the chi-squared here. I think it was something like 0.336 or something. And you can get the actual. So if we take a look at that graphic again, it's 0.338. And you can find out the area to the right of it, which is this right here. This is a crazy amount of decimals on it. But that is going to be the chi-squared p-value right there. And here's the chi-squared test statistic. Now, as the chi-squared gets bigger, what happens to the p-value? Larger chi-squared test statistics lead to what are p-values? So look here, larger chi-squared test statistics lead to what are p-values? Larger chi-squared test statistics lead to what are p-values? Lower, they're more extreme. There's less area to the right of them, and the chi-squared test statistic is found by finding the sum of the observed minus expected squared over expected, the kind of difference between the two squared, chi-squared, over the expected. And when you take the sum of the cell chi-squareds, you get a quantity of deviations, which is the sum of the deviations, and then you look to the area to the right of it to find the probability of something as extreme or more extreme than this sum of the deviations. And this would be an extreme one, but ours was very, very tiny. So it was a very probable deviation. A very probable deviation was seen because the p-value was high, meaning the deviations we saw are likely by random chance. Well, some practice with rejecting the null and failing to reject the null. You will have to write a statistical test or two. There are 12 points that are written on the test. So make sure you know how to do it. Okay, let's get ready for the leaderboard. Kind Llama, Fuzzy Dove, Radiant Cheetah, Agent Lark, and Diligent Panther. Here we go with the next question. What is your decision regarding the null? Now, you only have two choices when it comes to the null. There's only two answers on the board here that make sense. There are other ways to word them, but what are the only two answers when you talk about the null? When you talk about the null, you should only have two possible answers. What are your two answers? The two answers with the null are reject, no worries, Lillian, reject or fail to reject. And when I'll answer Space Cat in a moment here. Great job. Thank you, Space Cat, for the questions right there. When you reject, when the p-value is low, reject the null. When the p-value is high, just let it fly, just let it be. So the way you know how to do this is look at the p-value right here. If it's higher than your alpha, you let it fly. It's a high one. Since it's high, we are going to fail to reject the null. Any reasonable alpha level. The test would say like 0.05 alpha, 0.10 alpha, 0.01 alpha, and this p-value right there is way above, so you would fail to reject. We don't like the word accept because it sounds like we're saying the truth, but when the p-value is low, we reject the null. And Space Cat said, when a problem says the average number of blank, that means use proportions, right? It depends. If it says the average age of students, I'd have to see, Space Cat. It might be proportions. Like if it says, it would depend. Good question, Space Cat, right there. I'd have to see the exact instance of it. If it says something like, we're looking for females or in-state students, that's all categorical data. Always look to the variable type to see if it's proportions or means, because if it's proportions, it'll be a categorical variable we're looking at. And if it's means, it'll be a quantitative. Hey, Richmond, is that on Richmond there? Good to see you there. Yeah, always look to the variable type. And thank you so much, Richmond, right there. Where was alpha again? This one didn't give alpha, but and this is a good question, because you say, what if you use a 0.6 alpha? Really, in stats, the highest alpha ever goes. I know, right? It's so good seeing people in the chat I haven't seen forever. The highest alpha goes, really ever, is 0.10. I don't use that. And if alpha is not stated, always assume alpha is what? If alpha is not stated, assume alpha is what? This is a great question. Alpha is the point at which we reject the null. And if it's not stated, assume it is what? By the statistical standard. And people are saying in the chat, 0.05 right there, 0.05. That is what we assume alpha is unless we're otherwise stated. This one didn't state it, and reasonable assumption with alpha 0.05 unless otherwise stated. Boom, Joe knows some 0.05 right there, because that is what we always use in statistics. Unless someone's like, I want to use a 0.10 alpha because I really like type 1 error. Remember, alpha is also your type 1 error rate. So if you increase alpha, more type 1 error. I know. No, Adam. I'm pretty sure it's Adam right there. It is not time to feel old. I'm in my 40s. Oh, I'm in my 40s. That's when I'm still playing Pokemon. So that's when you start to feel old. Is when they tell you need hip surgery and you're like, but I'm only in my 40s. Fun stories. Anyways, continuing on. Leaderboard time here. Kind Llama, Radiant Cheetah, Diligent Panther, Glowing Dingo, Amazon Stork. And I will say this, and I do mean this. Always stay active, get good sleep, and eat healthy. Those are the best things you can do to fight age. Stay active, good sleep, good food, good mental energy, positive affirmations. Do that stuff daily, because you're just fighting father time or mother time. I don't know, something time. Just stay positive and do what you can to fight it. I'm still fighting it every day. Next question, here we go. How many degrees of freedom does this test have? And practice stats. Stats is the key to life. Take a look at this right here, and some of the test questions are about as easy as this. I know. It's so good to see you there, Adam. It makes sure I love the participating office hours. So we do have some questions that are a little bit easier on the test if you know where to look. Now, I like to do this formula by hand. We'll do some power coming up later. So I ask you to do this. Look at how many columns there are here. Just everyone start shouting in the chat how many columns there are. How many columns are there? Look at how many columns there are and tell me how many columns. Got a lot of time. 2. Look at how many rows there are. Start shouting at me in the chat how many rows there are. Look at how many rows there are. Same answer, right? 2. So that makes this a what by what. That makes this a what by what. Caroline already knows where we're going with this. I'm going to pin Caroline's comment right there. That makes this a 2 by 2. And the formula is rows, wow, clicked the wrong button, luckily I didn't do anything. It's rows minus 1 times columns minus 1. 2 by 2 becomes 1 times 1. There's 1 degree of freedom. There's also something really cool. One of my favorite things about this, I'm going to show it right after this, is it's kind of like a Sudoku puzzle. Degrees of freedom are needed to make calculations in statistics. If we run out of degrees of freedom, we can't actually create estimates for things. So they're actually super duper useful, but they're mainly a math thing. And really great job. We got to throw some wows right there.
Wow.
So let's take a look at how it looks like a Sudoku puzzle. So if you check this out right here, what type of written questions are on the test? Coming up here at the end, we'll talk more about that with interpreting intervals and interpreting tests. Someone give a random number between 1 and 50 or 0. Give a random number, like as though you are freely choosing that number. 13. So if this is 13, this is 37, this is 37, this is 13, because they have to add up to 50 and 50. How many of these numbers did you freely choose and then everything else was a forced choice? How many numbers were freely chosen? 1. Because this has 1 degree of freedom. Since 1 degree of freedom is all we have, every number is a forced choice, and that's kind of how it works. It also works the same way with the mean when we do n minus 1. Let's say these numbers average up to 10. Pick 2 numbers at random, but don't make them too crazy. Pick 2 numbers at random, and they average up to 10. The average of these numbers is 10. So pick 2 numbers at random. 3. What else? What else? Don't go too crazy. Yeah, give me one more number. 7. So how many of those numbers were freely chosen? If the numbers average to 10, there's how many degrees of freedom for the mean? So this is the row minus 1 times column minus 1 degrees of freedom. This is the n minus 1 degrees of freedom. We'll highlight the degree of freedom formula right there. That's the degrees of freedom for this one, rows minus 1 times columns minus 1. And then the bottom for the one sample t is n minus 1 degrees of freedom. When do we use this again? Why did we choose random? It's to illustrate the concept of degrees of freedom. You will never actually usually have to show this off, but the idea of the one sample t having n minus 1 degrees of freedom, and the degrees of freedom are basically for calculation purposes when we have to figure out estimates for coefficients in models. But additionally, the degrees of freedom tell us the what of the t or the z. Last comment here, the degrees of freedom tell us the what of the t or the z. The degrees of freedom tell us the what of the t or the z, the shape of it. And interestingly, the t and the z both become way more normal with more degrees of freedom. More degrees of freedom, they become more normal. You see the classic 1.96 if we go to the between. So eventually it goes towards 1.96. We'll just add a bunch of zeros and it'll be right there, 1.96. So the t and the chi-squared, excuse me, I think I said z for a moment, the t and the chi-squared become more normal, and the degrees of freedom tell us the shape of these distributions. T created by William Gossett. I don't know, Mendel might have just done chi-squared, but he did the p-plan stuff, so he might have did chi-squared. Next, leaderboard. Here we go with Kind Llama, Radiant Cheetah, Diligent Panther, Glowing Dingle, and Amazon Stork. Next question. What is the null for this test? One of my favorite tests to do the null for. Wait, so Z, but not Z has no degrees of freedom. Emma, sorry if I misspoke. Z does not have degrees of freedom. It's called the Gaussian curve, and it's one curve only. It's just the Z normal curve. So the Z does not have degrees of freedom. The T has degrees of freedom. The chi-squared has degrees of freedom. The F has degrees of freedom. We didn't even cover the F, but it does have degrees of freedom. Numerator and denominator has 2 sets of degrees of freedom. So this is one of my favorite tests to do the null hypothesis for, because you go right between the words and what do you write? So what do you do to write the null hypothesis right here? You go right between the words and you write what? If you see this on the test, you go right between the words and you write what? Like right off my screen, I can't even get to it. What do you write there? You go right between the words and you write independent. The null hypothesis would be breaking a bone, they put independent between it, is independent of someone's gender. The alternative hypothesis, you just change it to say breaking a bone or gender is independent. This would not deal with the mean because this is not what data. Why would this not deal with the mean? Because this is not what data. Technically, you can do the average of proportions, but we don't like to say it's not, because this is cat data, it's not quant data. So the null hypothesis, we just put independent. And think about what the test is called. It's called the chi-what? What is the chapter called? We call this chapter the what. So if you remember what the chapter is called, you can be like, wait a minute. The null hypothesis makes sense now because the test is called the chi-squared test of what? For 1,000 points, it's called the chi-squared test of what? The chi-squared test of independence. So the test itself is the name of it. And so the chi-squared test of independence, really good practice right there. Remembering the name of the test can help and be like, oh, we're testing to see if the 2 variables are independent because this is chi-squared test of independence. Really good notes right there and good practice. Leaderboard time. Kind Llama, Radiant Cheetah, Glowing Dingo, and Fuzzy Dove with Rocky Lobster. Got Elvis right there and a dingo. So next question, what is the alternative for this test? I can't remember if it's the same test or not, but you got it. Just remember the null hypothesis, a lot of time on here. So when it's quantitative data, it's independent. Be very careful, Caroline. So this right here, this is the chi-squared test of independence. So the null hypothesis for a mean is mu equals some hypothesized value. The null hypothesis for a proportion is p equals some hypothesized value. The null hypothesis for the 2 sample t is mu1 minus mu2 equals 0. We can test other values than 0, but the most common value tested is 0. So you could write mu1 equals mu2. The null is that the means are equal. You can test other values, but usually we just test to see if they're equal. The null hypothesis for the chi-squared test of independence is put independent between the words, which you could also say not associated. There are other ways to phrase it, like gender is not associated with breaking a bone. But remember, There's not one way to write the null. It depends on the data you're working with. So for proportions, the proportion of females at UT is 50%. For means, the mean age of students, the true mean age of students is 20 at UT. For difference in means, mu1 minus mu2, the difference between GPAs of UT and Florida students is 0. Who knows? Sorry, Florida, we're always here to do a little picking on Florida. And then this one, put independent between. Does that make sense, Caroline? Depends on what test you're doing. There are going to be written portions. Stay tuned towards the end. You'll have to write out two different things. You'll have to have two different things to write out. What two different, put it in the chat right now, we'll pin it. What are the two written portions that you're going to have to know how to do? Does anyone know as we take a look at that leaderboard? There are two written portions that you have to be able to write out and know how to do that we've been practicing a lot in class. You have to write out this and you have to write out this, which we'll practice coming up later. Two written things with, as we talk about, kind llama, radiant cheetah, glowing dingo, fuzzy dove, and charming quail. We have right here rejecting and failing to reject the null and confidence intervals. Great job, Savannah, right there. You have to do test interpretation and you have to do confidence interval interpretation. 12 points on the test interpretation and confidence interval interpretation. Check out as we keep working here and practicing. Find the missing value. Get your calculator if you don't have it. 90 seconds to go. What are you looking for on the screen? You're looking for a what value. This missing value on the screen is a what value. That missing value on the screen is a what value. It's an expected value. The top one is the count, which is the observed. We observed 258 females who were born in Tennessee. The next one is an expected. How many you would expect by random chance given the null is true. The next one is the cell chi-squared, which is the standardized difference between the observed and the expected. Rather, they're observed minus expected squared over expected. These are the row totals, these are the column totals, and this is the grand total. Now, my favorite way to do this formula, and I'll take over the screen right here so we can do it. Why are you off the screen? Oh. So when you have a missing value, know your formulas. Take a look at how people did here in a second. With your formulas, you are trying to find an expected. Expected is row total times column total over grand total. To find this, you circle the row total, the column total, and divide by the grand total. Look at how it makes an arrow in on the number that you're looking for, and simply multiply those numbers. So this will do it right here, the row total times the column total over the grand total. For 5,000 points, does anyone remember the trick I mentioned in class to confirm your work? So now that we have the answer, how could you confirm your work? We'll see how the leaderboard did here in a second, but there's a trick, like 261.895. What is the trick I mentioned in class about these numbers right here? Add them together, right? If you add these together, it should add up to this right here. So we can see if this number right here, you can also subtract to get it. If we add 159.105 and you get 421, just some decimal differences due to probably just off not carrying enough numbers with the other one. But that's got it right there, 261.895. And know how to solve these, know your formulas, know how to look. Yeah, and you can do that right there, Daniel. Daniel, great job. Yes, things like that. If you know how to get it and you can get it quick and you're like, well, this got it, then you can check it. Are we allowed to have a formula sheet? Yep, you can print out or write down the formula sheet for the test. So print it out, write it down, know the formula sheet. And I can't suggest this enough. I'm gonna give another shout out to my videos I have right here. If you want, not review 34. My best suggestion is if you don't know the formulas and you want to know all the notation, check this out right here. Hopefully don't crash again. So go here, check out these videos. And if you go to the chi-squared test of independence, what you'll see is I will list out and all the notation. And every bit of it, I'll talk through. I'll do a full example here with all the conditions. I'll solve all the expecteds by hand, all the cell chi-squareds by hand. I'll sum up the cell chi-squareds. I'll find the degrees of freedom. I'll plot the p-value. I'll fail to reject or reject. And I'll even show how to do it in JUMP and show the end result. Any test like here on the two sample t-test,
we have here,
I'll go through it again right here. You'll see I'll talk through the notation. So you can see all the notation for the two sample t. Everything notated for you. Degrees of freedom, complicated formula. There's the null hypothesis and the alternative. Writing down the test, clear notation for you to see. Like, I want these things to look very clear, solving it out, degrees of freedom solved, plot it, and state the conclusion. Look at this right here. Do you think we reject or fail to reject the null? You should be able to look at this point if you know how to do statistical tests and tell me reject or fail to reject. Reject or fail to reject. 5,000 points. Crazy points right here. Reject or fail to reject. Fail to reject, Mally got it. Yep. Do you have any guess at the p-value? Take a look. It's above -1, so it's got to be a little bit larger than what? P-value's got to be a little bit larger than what? Because it's above -1. It's to the right of -1. So use your chapter 5 knowledge and be like, well, it's to the right of -1, so it's got to be a little bit bigger than this. For 1,000 points. P-value's got to be a little bit bigger than what? Maybe a good bit bigger. We can go find out exactly what it is, but think about your rules of the empirical rule. So the p-value should be a little bit bigger than what? How much area is shaded on the curve? That's what the p-value is. It's the probability of something below that line. Just take a guess if you don't know. The p-value is probably a little bit bigger than what? Well, not 1. Remember, 1 is the maximum. Good guess right there. We'll 30 points for a guess. Not 0.5, because think it's not more than half the curve shaded in. It is bigger than 0.05. But does everyone remember the 68, 95, 99.7 rule? That's where we get p-values from. Reese, decent guess right there. And this just keeps creeping up the screen. Now I can finally grab it and bring it down here. Lillian's on the right track with this. Lillian has a very good guess. Lillian is on the right track. We'll throw more points. Because check this out. If we bring this over here and we were to do the 68, do you know how when we do 68, it's in here? 68% is in here. Anyone have another guess? It has this area right here that I've shaded has to be a little bit bigger than what? Now take another guess. The area I've shaded has to be a little bit bigger than what? The area I've shaded in yellow has to be a little bit bigger than what? One more guess. These are the things I want you to see in statistics and be like, oh yeah, chapter 5 comes in use. Any guess? Don't worry about being wrong. That area has to be a little bit bigger in yellow than what? Boom, Erica said it right there. 16. Lillian said too. 16. Because the area below -1 is 16. And little Mojo, it probably, Mojo's got a good answer right there too. It's probably about 20%. Yep. It's because the empirical rule was 68 in the middle, then there'd be 16% in either tail, so it has to be a little bit bigger than 16. And so a lot of times when you're running tests, if you just look at that, you will know the answer. If you've done enough statistical tests, you'd be like, well, that's a pretty large p-value, so we don't reject the null, we fail to reject, because what we saw was very probable, large p-value. Kind llama, glowing dingle, dingo, dingle. I got up at 3 a.m. this morning. I got up at 3 a.m. yesterday and 3 a.m. Wednesday in the 3 a.m. Okay, it was 3:30, so bear with me. Radiant Cheetah, Fuzzy Dove, and Lucky Hair. I've woken up in, tomorrow I'll wake up in a 3rd state. New York, Virginia, Tennessee. Here we go. Find the missing value. Next question. Here we are with the missing value again. You are looking for a what? What missing value are you looking for? Catching planes. I was on a plane today. Flew so really quickly on that. So you're looking for a cell chi-squared right here. Wednesday we woke up, we went to New York. My wife was up at Cornell for a conference. I got to visit. It's my parents' alma mater. So it was really cool. Got to like check it out and go around campus and got a tour. They've got a really cool food science, which we have at the Ag campus here too. I got to try their ice cream. Should have bought some of the cheese. They've got Big Red cheese up there. Big Red, it sounds like gum to me. It's like Big Red, but that's what they are, the Big Red Cornell. And so got to go around the campus, really beautiful campus. I do like Rocky Top better. Very hilly campus. I'm telling you, like, everywhere is a hill. Whole campus is a hill. So nicer campus to walk here. They got a good view or two, because they got like Yucca Lake they got this really cool view. I got a picture of it or two. Went up there and then flew in and saw my nephews. Oh no, Bryn. Oh, you should go up to Ithaca. Go up to Ithaca. You'll upstate New York, Finger Lake area. But yeah, so then I went and saw my nephews and my cousin, or not my cousin, my brother. And then we flew back, but we were catching like early flights. Our flights were in 5 a.m. We had to get to the airport an hour early, and then the airport was like 30 minutes away. So this formula right here, let's do it. Please, please, please. What do you think I want you doing? W family right there. What do you think I want you doing while I do this? What do you think I want you doing if you're watching this video right now while I do this? What do you think I want you doing? What would make Brian's day right here? Write this down, follow along. What you want to do on the test, you see cell chi-squared. You immediately go look at what? You see cell chi-squared, you immediately go look for what? You see cell chi-squared, you immediately go and look for your what? You're like, oh, I gotta find a cell chi-squared. I should probably go look at my what? My formula sheet. So now you're looking at your formula sheet over here. Boom, you go to the formula sheet. You say, oh, cell chi-squared. It's this formula right here. You see where it says, this is, and you have to know this, this is a cell chi-squared right there. That's one of them. That's a singular cell chi-squared. Oh, it doesn't say, yeah, you got to sum them all up to get the chi-squared test statistic. That's a singular cell chi-squared. So now we have to go and find the observed. But notice there is no observed up here. Where is the observed? Where is the observed? For males, where is the observed amount of males? We're trying to calculate a singular cell chi-squared, which is, we'll sum them all up. We're trying to find this value right here. Actually, we should just put it in yellow because we started circling in yellow anyways. That's in yellow, and we're trying to get that singular cell chi-squared. It is the count. Yep, the count right there. So it's going to be this is the count, and then the expected is this right here. And there we go. And just plug in the numbers. So at this point, if you know the formula, you just take the numbers, plug them into the equation. And we're just going to do a rounded version to make it nice and neat. So that's basically 16, or we'll solve it in the calculator more exactly, because that's what you do on the test. You go right here and you go 128 minus. Now, if you're wondering the reason we square it, it's so everything is always positive. If you didn't square it, the deviations would actually go to 0. And we don't want that. We want to get a sum of the deviations. So you square it so they're positive, and there is the cell chi-squared. Now, if you had the rest of the output, you could actually add up all these values and then figure out what is missing. So the way you get the full chi-squared is you sum up all these cell chi-squareds. The sum of the cell chi-squareds is the full chi-squared test statistic. So if you were to see down here a Pearson value, you could just subtract from the Pearson chi-squared the other values and find out the missing cell chi-squared. That one's a little bit longer, but there's many different ways to get this if you know how to do the output. Any questions on this one right here? Know how to calculate these. Just try it, practice it. Understand what you're looking at in this output right here. Know that the count is how many people you see in each group. Like I saw 163 females not born in Tennessee. 159.1 is how many we would expect by random chance. Row total times column total over grand total. Cell chi-squareds is a metric of deviation within that cell of the observed and the expected, and then the other things, but the row totals and the column totals and the grand total. Good work, good review. Here we go with the leaderboard. Kind llama, fuzzy dove, glowing dingo, lucky heron, charming quail. Next question. What are the degrees of freedom for the one sample t interval? Should be nice and easy. Let's zoom in on a little bit more if you can't see it. You should know it, seeing it right there. Anyone want to type the complicated formula in the chat? Not the complicated, the not complicated one. Anyone want to type the one sample t degrees of freedom? The one sample t, Savannah already did it, it's n minus 1. It's n minus 1. One sample t is n minus 1. Two sample t is what? The one sample t is n minus 1. The two sample t is what? The one sample t is n minus 1. The two sample t is what? It's too complicated. And that's why we use applets for it. No one really ever solves the two sample t degrees of freedom by hand. If you're wondering what it is, the two sample t degrees of freedom, if you wanted to solve it by hand, if you're really like, I want to, it would be this right here. Here is the 2 sample t degrees of freedom. It is too complicated. Uses the standard deviation and the sample sizes for each group. I just say it's too complicated, and you're not going to solve this one by hand on the test. We don't even give you the formula, but it's the 2 sample degrees of freedom for the 2 sample t. The 1 sample is n minus 1. Daniel's all afraid right there. Sorry, Daniel, didn't mean to scare you. Next, leaderboard: kind llama, fuzzy dove, lucky hair, glowing dingo, and charming llama. There's 3 times we have to find degrees of freedom. So Nia, good question right there. What are the 3 times we have to find degrees of freedom? See if you can list them and know the equations. What are the 3 times you have to find degrees of freedom? We don't really make you find p. Well, if you find p-values, you have to logically figure them out sometimes. I think I have one of them on the test right here. Look to Canvas content. n minus 1 for the 1 sample t. Great job, Aiden, right there. And then also rows minus 1 times columns minus 1 is the chi-squared test of independence. We'll make Aiden a mod. Good answers, Aiden, right there. That is the chi-squared test of independence. And then the 2 sample t is the too complicated one we just showed. So Nia, good job right there. The 1 sample t test, n minus 1, and the chi-squared test of independence, rows minus 1 times columns minus 1, and then the one we'll never have you do on the test other than asking you theoretically. It's a complicated equation. It's the 2 sample t, which is the complicated equation we just saw, and it's called the Welch's 2 sample t for unequal variance. Let's do the equal variance one. I don't know how many questions, 43 or so, somewhere around that. Next question on this Kahoot with 26 questions. What is the missing p-value? Now you have to find a p-value. Take a look at the test. What is the missing p-value? What is the missing p-value? Now, p-values have to be between what and what? A p-value has to be between what and what? A p-value has to be between what and what? 0 and 1. Whatever you find, whatever you enter in, type in, has to be between 0 and 1. Now, the p-values share an interesting relationship. At 30 seconds, I'm going to go and start solving. I might do that for all these 90-second ones I put in. But p-values have interesting relationships because there's how many alternatives? How many alternatives are there when doing a statistical test? You don't use all of them. You pick one based on the researcher's question. So on the researcher's choice, they choose between one of 3 alternatives. So when we are doing p-values, it's based on the sign of the alternative, whether we do a less than, greater than, or not equal to. When you do a less than, you shade to the what? When you do a less than, you shade to the what? So think about it. When you do a less than, you shade to the what? You shade to the left. When you do a greater than, you shade to the right. When you do a does not equals, you shade both sides. So if you were to land all the way down here on this curve, then the less than would be this p-value. The greater than would be this p-value. The does not equals would mean you reflect on this side, and I kind of did that poorly right there. Much better. So think about this. What would the p-values be if the p-value for the top one is 0.07? What are the remaining p-values? What are the remaining p-values for the next 2 tests? What are the remaining p-values? Great job, Reese, right there, knows the answers instantaneously. And you can see visually now how they look, that this one is always double the smallest. So it's 2 times smallest. Whichever one is smallest, the does not equals is a reflection on the other side of the smaller one. And then these 2 add to 1. So the less than and the greater than add up to 1. And you can see that right here because you've got these 2 shading left and right. The 14 is double the smallest. So you take right here and just merely double on the other side the smallest. So it's a reflection on the other side of the curve. So you just take that right there. So the does not equals test is double the smallest, and the less than and the greater than add up to 1. And if you look at which p-value we're missing right here, the p-value we are missing is the what test. So which test were we missing? The less than, the greater than, or the does not equals? Which p-value were we missing? The less than, the greater than, or the does not equals? Which one were we missing? Take a look at the signs right here. It's a little confusing, but we were missing the what test. The less than. This is the less than, this is the greater than, and absolute value means either side, greater than the absolute value. Like if there was a negative, it would go over here, and also it'd be the same if it was positive as absolute value. So this is the does not equals. This is the does not equals. This is the greater than. This is the less than. Does that make sense where these are? P-value, 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 less than, greater than, does not equals, and just subtract from 1, and you get the less than test right there. So there is the answer. Pretty good job. Leaderboard time. Kind llama, fuzzy dove, lucky hare, radiant cheetah, and glowing dingo. Next question. Let's do this. Find the missing p-value. Let's see if you can do it. This is a test of your knowledge, so it should be pretty quick. Which test are you missing right now? You are missing the which test right now. Which test are you missing? Which of the tests are you missing? You might hear me talking to me missing. Gotta resend that. Say starting in about 30 minutes. Missing the does not equals. Oh no! So the does not equals test is always what the what is p-value. The does not equals test is always what the what is p-value. I like right there the math right there, Mally. Nice job, William, right there. It's always double the smallest. Double the smallest. So if you notice right here, we have the smaller p-value right here. If you double it, and wow, really good job right there, everybody. I'm impressed by that. A lot of people got it. Double the smallest p-value right there. So make sure to know that the does not equals is a reflection on the other side. Try drawing these things out. The more you draw it out, the more you do the work yourself right here, the more you remember it. And then just try writing this, try remembering it. It really, and I promise you this, you're never gonna learn piano watching videos of people playing piano. You'll remember that much. If you sit down and play piano, you learn it. So sit down like me, like I did over the weekend, play some piano, learn some stats. It's an analogy. Sit down and learn some stats. Try drawing these things out that I draw out, try doing different values, and then you'll remember it better because you'll create more memories of doing it. And then you'll be like, oh yeah, I was writing that down. Oh, that's what it is. It's a lot easier than hearing me say it 10 times, which I will say it 10 times. Leaderboard time. Kind llama, fuzzy dove, lucky hare, radiant cheetah, glowing dingo. Here we are with the next question. What is the missing T ratio? A lot of people get stuck on this one. So the missing T ratio, how would we find it? And you can get this one really quickly. I want you to notice the T ratio is an equation. It's the whatized. For anyone who's answered, the T ratio is the whatized. The T ratio is the whatized. What is the T ratio? If you say it, then you basically know the answer, because it's basically on the screen. The T ratio is the whatized. Thoughts on that? I'll answer it at 40 seconds. If you know it, the T ratio, which is the T statistic, is the, oh no worries, it's the difference standardized. It's the difference standardized. So if you go to the formula sheet, you will see the following. On the formula sheet, you have the following where it says to find the T statistic, great job Autumn right there, y bar 1 minus y bar 2 over standard error of y bar 1, y bar 2. Well, do you see any of this on the screen? Great job, Mally, right there. Do you see this? Y bar 1 minus y bar 2? Do you see this? I mean, what is that? That's two means, and you're taking their what? What is that? That's the difference. That's literally just the difference between two means. That's the difference. And do you see the standard error of the difference? That says standard error right there. That's SE for standard error of the difference. That's subscript of the difference. Do you see that on the screen? If so, where? Where do you see that? Because we're trying to find the ratio of it, which is the t statistic with degrees of freedom that are complicated. Like those are those, we're not trying to solve that, but those are the degrees of freedom of the t. So do you see this green thing anywhere? Where's the green thing at? Because we're trying to get this value over here. Where is the green thing? Because this thing right here, if we know where that's at, we could solve this equation, which that thing right there is this equation of square root s sub 1 squared over n sub 1, s sub 2 squared over n sub 2. We could go find all that. It's just the standard error of the difference. It's right below right here. That's right there. So there's the standard error of the difference. So if you literally just take those numbers and divide them, that's the t ratio. And look, it's basically like negative 2.3, or you can do that and move decimals. There you go, right there. Move decimals, basically negative 10. And if you notice, it's way off the curve at negative 10. It's a t statistic of about negative 10, and the p-values are basically 0 down there. Is this, who feels like this makes a little more sense right now, because it's the difference standardized in this test right here, and then you can visually see the t. You can literally see where the t is at because it marks it on the curve. And when you see this t all the way down here, you know it's an extreme negative t. This is not the value of the t. This is actually in units of the problem right there. But if you think about like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 standard errors, you could count out your standard errors because the curve really only goes to about 3 standard errors on the end of it. So be careful. The bottom of it is the units of the problem. Great job, Lillian, right there, and everyone. I'm glad it's making a little more sense. At the end of the course, like, wait a minute, this is what this stat thing is doing. We hope it helps you in a lot of your courses, your major, even if it's not business analytics. So it's negative 9.93. Pretty good job. Remember to look at the formula sheet. Let's go on to the leaderboard here. Kind llama, radiant cheetah, fuzzy dove, lucky hare, glowing dingo. Next question. What is the missing value of difference? So now think about this. You know the ratio here, it has to be a negative difference. You could also cheat and look over here. But think about the equations and how to backwork this. Because you basically have x here. X over 0.023 equals to this right here, which can kind of tell you how to get it. I don't know if we still have a question quite like this, but also the answer was on the previous slide. But it's a solve for x where it's the difference divided by the standard error is equal to the t ratio. So I guess you could just multiply both sides by 0.023, right? So then, because it's x over 0.023 equals negative 9.93, so multiply by 0.023 and you will get the answer of about negative 0.23. Also, you know it's a ratio of negative 10, so that thing has to be 10 bigger but negative than the other one. So you could times it by 10 and do negative. So pretty good job. It's kind of the same answer, so I might not go into too much detail. It's the same output, knowing that those things, the difference over the standard error is the t ratio. Leaderboard time. Kind llama, fuzzy dove, lucky hare, radiant cheetah, honest dove. All the doves are here. Next question. What is the null hypothesis for this test? Ooh, I love this. Now, this is an easy one. There are 26 questions on this, and we're pretty far into it. So we're pretty far into the review, probably about another 15, 20 minutes. Say it with me. The null has the what sign? The null has the what sign? The null has the what sign? Code's down at the bottom right there, William. Code's at the bottom, 2454156. The null has the equal sign. The null has the equal sign. There are 3 alternatives, and how do we pick the sign of the alternative? How do we pick the sign of the alternative? Is it the data or the researcher question that picks the sign of the alternative? How do we choose the sign of the alternative? Is it the data or the researcher question? Researcher's question. Whatever they're analyzing, they come up with this before they even collect data. They're like, is there evidence of this? Well, let me go and collect some data and look into this. And they're not gonna look at the data and say, oh, let me go this way. That is called p-hacking. John Oliver did a great segment on it, and we don't do that. We don't do p-hacking here. That's what we do here. So this is a what test. Does anyone know what kind of test this is? There's a hint up there, but this is also a what test because of this. What kind of test is this where we're looking at the difference between these things? So we have males and females, and I think we're looking at GPA differences. It's a 2-sample T. Great job, Justin, right there. And it's a 2-sample T. We're looking at the differences of GPAs of males and females. Which group had the higher? Great job on the null right there. Which group had the higher GPAs in the sample data? So notice that the difference is negative. So which group in the sample data had the higher right here? Which group had the higher mean in the sample data? Since it's negative, it goes with the one with the negative sign. It would actually be females right there because the difference is negative. Think about like 8 minus 10. 10 is bigger, it makes it negative. So like, I'm just making up fake numbers, like 8 minus 10 is negative. So this would be that the females had a higher GPA on average in the sample, and the interval is also completely negative. Are you ready for this? I'm gonna write it in the chat and pin it. I am blank % confident that the true blank is contained in the interval blank to blank. Now be careful. I'm going to throw another 5,000 points. Can we hear the music? If anyone can interpret this interval. Now the music doesn't go through. Now this music doesn't go through. I can hear it. Nice music. Oh, I'm going to have to rework things. What I do to my setup. I am 95%. Ah, but that's not the. You might be typing more. Lillian might have ran out of characters right there. Remember, when interpreting an interval, it'll have a lower and an upper. I think they hit enter by accident. Yeah. Basically, and you could say, no worries. I was like, I think Lillian's typing more. I was like, I think Lillian 5,000 points. First one to answer right there. And if you're seeing Lillian write this here, I want you to try to do it too. We are 95% confident the true difference in means of GPAs of males minus female. I would say it that way. So that the graders should give you full points for that because you're saying of males minus females. The true difference in GPAs of males minus females. So this right here is the true difference in GPAs. Try writing it again for another 5,000 points. Everyone just practice this right now. I am 95% confident the true difference in GPAs of males minus females is true difference in means of GPAs of males minus females is contained in the interval. Which right there, Caroline's practicing. I am 95% confident the true mean difference in GPAs. This one's a difference in GPAs. So you got to make sure to say difference, Emily. Good job. And this is why I practice with people right here. Got to make sure to say difference for this one, though. That's one of the key words. So you need to have the males minus females. Emily, they might give you points for that. I could see Emily's. Caroline and Emily, really good practice right there. Emily's, I think you could argue it. Caroline, make sure to have difference in there or the equation. The difference of males and females. Males minus females or males and females. So we'll have one more person practice right here. And this is really good. I like doing this because then I can give you little tips because it's tough. You make a little mistake and lose points. I am 95% confident that the true difference in GPAs of males and females is contained in the interval. There we go. I am 95% confident that the true mean difference in GPAs of males minus females, make sure to mention that, is contained in the interval. So I am 95% confident the true mean difference between males minus females, true mean difference of GPAs. There we go. Caroline, thank you so much. I think Caroline did a correction right there. And remember, this is only for the 2 sample T. This is not for proportions. This is not for tests. This is not for means, singular means. Does that make sense? We're throwing out crazy points here these days. It's gone crazy right here. Okay, let's do the next leaderboard. Kind llama, fuzzy dove, lucky hare, honest dove, glowing dingo. Next question. What is the alternative hypothesis for the 2-sided test? So when you do the 2-sided test, what is the alternative for a 2-sided test? Which is when we shade both sides of the curve. The 2-sided test has the what alternative? What is the alternative for the 2-sided test? Now remember, it's the researcher who picks this alternative, and it also goes to the way you find the p-value. Great job with the not equal right there. So one thing I want to point out, and who can solve the t-ratio right here? Who can show the math to get that number right there? Just for practice, once we're going to review, what could you use on here to get that number right there? So how could you find that number right there using numbers on the screen? You can just type, don't worry about all the decimals, just, just show you know where to go. Like if that number was missing right there, you could just, yeah, and then Nia's doing a great job right there. We'll make you mod too. And Lillian, great job. Yep. How also do you know that there's a difference right here? What is good evidence of a difference besides the low p-value on the does not equals test? Like, what do you think is good evidence of a difference in GPAs? That we have evidence of a difference. What do you think is good evidence of a difference? I'm throwing in additional questions. I'm asking for something about the confidence interval. Why do you... Will the alternative hypothesis for two... Yeah, the two-sided, and that's not a two-sample. Caroline, good question. That's not a two-sample for two groups. That's a two-sided. So be very careful. Two-sample is not two-sided. Two-sample means two groups. Two-sided means does not equals alternative. Does that make sense? Two-sample means comparing two groups. Two-sided means doing a does not equals alternative. So be careful between two-sample, two groups. Two-sided does not equals alternative. So the two... It just means, you know, are you shading both sides of the curve? Two-sided. Do you have two groups? Two-sample. So just make sure right there. Are two-sided and two-tailed not the same thing? Two-sided goes to the sign of the what? If you say two-sided, you're talking about the what? Two-sided goes to the what? Explain in the chat. Two-sided means you're talking about the what? When we say two-sided. If someone says I'm doing a two-sided test, what does that go to? A two-sided test. Oh. Or if you're wrong, just take guesses. Purposely not putting my head right there. Not two groups, the two-sided, and Reese has it right there, and good answers. We're throwing a bunch of points out. The two-sided, and great job, Justin, right there. The two sides of the curve are shaded, and this means the p-value that does not equal sign for the null hypothesis. So the two-sided, but here's the thing. Going back to our notes, let's go back to this thing we did way earlier. Here we are. Is this it? Here it is. You could do a one-sample t-test that is two-sided. You can do a two-sample t-test that is two-sided. You can do a one-sample z that's two-sided, two-sample t that's two-sided, one proportion z that's two-sided. The sample part of it goes to how many groups there are. So when something is two samples, there are two groups. Do you see the two groups right here? So when we say two sample, do you see the two groups that are being tested for the two sample? Just like point, what are the two groups that are being tested for the two sample? One's on almost near 1 million points. Crazy. Males, females. Now, the GPA makes it a what test? The males and females makes it a two sample, two groups. That's what we mean by two samples, two groups. And the GPA makes it a what test? Caroline's right with quant, and so quant means we're doing what? This is GPA, we're doing what? We're testing means, right? Mr. T. Males and females make it a two sample and GPA makes it a mean test. Caroline, perfect answer. And then we decided that the alternative would be two-sided, which means we're picking this p-value right here. So when you say a two-sided test, that's just talking about the sign of the alternative. One-sided means less than or greater than, and we can show this off also. Think about why we call it a one-sided test. Does everyone see a little bit better where the one-sided tests are? Which of these are the one-sided tests? Which of these on the screen right here is the one-sided test? Where are the one-sided tests? Where are one-sided tests? Where are the one-sided tests? Yep, these are the one-sided tests. They only shade one side. Here is the two-sided test, the two-tailed. Two-sided does not equals. So the two-tailed goes both ways right there. Right? Sometimes I like to do it like this, where I do a little arrow this way, little arrow this way, because this one shades to the right, this one shades to the left, and they're only one-sided. So the top are one-sided tests, and the bottom is a two-sided test. So make sure to know the lingo of like one sample, two-sided, one-sided. The sidedness goes to the shading of the alternative, and the two-sample goes to two groups. And great job right there, Christina. It's a means test because GPA is quantitative. Another 1,000 points. Christina also making you a mod right here. Appreciate these answers. It is a means test because GPA is a quantitative. We're comparing the means of both groups. Now for 5,000 points, we could visualize this comparison by showing what? For 5,000 points, we could visualize this comparison by showing what? For 5,000 points, we could visualize and show the comparison by doing what? We could visualize and take a screenshot of this if you don't have it. This is all the graphics. Visualize and show the comparison by doing what? We could visualize and compare them. Not a scatter plot. Good answer. Not a scatter plot, though. Not scatter plot. Don't worry about being wrong. Boom, Lillian said it. Side-by-side box plots, because male and female is categorical, and then GPA is quantitative. You see how it's quant up there in the Y? The Y variable of interest is quant. And then to visualize this, to visualize categorical male, female, quantitative GPA, you can do stacked histograms or side-by-side box plots. Scatter plots are only for what combination. You know what to type in the chat if you're in my class. Scatter plots are only for what combination. Scatter plots are only for what combination. Scatter plots are only for what, which is the first condition of regression. QQ straight enough, no outliers, plot doesn't thicken. QQ, quant. So I love that right there. So these are all the visualizations, like mosaic plots are categorical. And I do have the top one being the first one we would choose. We don't do logistic regression in this class, and no one likes ring charts. Ring pops, not ring charts. That's a quote somewhere we have. So next question, leaderboard first. Kind llama, fuzzy dove, lucky hair, and honest dove, and glowing dingo. Here we go with the next question. Interpret the difference. I want you to put in the chat right here, see if you can do it. That difference right there is negative. Andrew Wynn is the best. I love it. I miss Andrew Wynn. He's not. Another quote. So we already talked about this a little bit, how since the difference is negative, it means which mean is higher. So if you were to take the sample differences right there, this won't be a short answer on the test, but it is important to know that this difference right here being negative means that which of the means was bigger. Yep, t-tests are for means. Females, no, U-Bot's got too many quotes. It's a good thing. Females had a higher mean than males in GPAs. True. Bless me, bot tells a joke right here. And once again, please check out, please check out review 3. I'm gonna pin it again in the chat. I cannot advertise it enough. The mean for females is this much higher than the mean for men because the difference is negative. And if there's a negative difference, that means the second mean over there is the higher one, the negative one right there. That is what we have right there. So going on to the leaderboard, we're gonna do 320 coming up here soon. Kind llama, fuzzy dove, lucky hair, honest dove, and glowing dingo. Next question. Story time. The null hypothesis is that it's a twig. So you're walking through the woods right here and you see a whole bunch of sticks and you're freaking out. You're like, you know what? I've been bitten by a snake, but I know most things are gonna be twigs out there. And then you're like, wait a minute, what is this right here? And you think, oh no, and you make a type 1 error. What did you do? So we have a very important thing to do right here. We have to review a type 1 and type 2 error. Please do this. In a type 1, the what is what? You never heard me say this before, you won't know what we're talking about. But who knows this? Maybe you've already answered it, but tell it in the chat to repeat it. And our people are saying it. In a type 1 error, the null is true and we reject it. In a type... What's the other one? We're going to say the answers here in a moment. And then we're going to show how this is done. What's the other one? In a type... The null is... And we... What is it? If you fill in the blanks, you remember more. In a type 2 error, the null is false and we fail to reject it. It's the easiest way to remember it ever. Thank you, Hannah, in our department, who made this up years ago. So in a type 2 error, the null is false and we fail to reject it. So if you ever get a question like this on the test, you need to write down the null and you need to say it and look at it while you're saying it. So guess what we're going to do right here? The null is a twig and we're going to make a type 1 error. You know what we do? We write down the null. We say null is twig. Alternative is snake. Snake. So here we are with the null that it's a twig. In a type 1 error, the null is true. What does that mean? In a type 1 error, the null is true. So what does that mean? What does this mean? In type 1 error, the null is true. It literally is a twig. So does that make sense? Type 1 error is a false positive. And so if it's true that it's a twig, it is a twig. Does that make sense? It is just a twig on the ground. That's all it is. I think Jaden's seen it right there. And we what it. The null is true and we what it. So what are we going to do this null in a type 1 error? What are we going to do to this null in a type 1 error? The null is true and we reject it. So we're going to reject the null right here. We'll put a little little purple on it. We're going to reject the null. And we think we have evidence for the alternative. So can you imagine this? This is when you're walking through the woods and you go, ah! But wait, what happened? Exactly. Exactly. Does that make sense with this type 1 error? You say, oh my gosh, I just had a type 1 error. You say, whoo, whoo, type 1 error. Now I had a type 2 error when I was doing archaeology back in the day. There were all these like down wood over here. So there was all this down wood like this. And then I was like over here. And I had a type 2 error because I said, well, I'll just take this shortcut right here. So what happened to Brian with his type 2 error right there? In a type 2 error, the null is false and we fail to reject it. So the null is false. This is false right here. This is false. This is not true, which means there it is. What this is right here. But we're not going to reject the null. We're going to retain it. We're going to not reject the null. So what happened to Brian right there with his type 2 error where he failed to reject the null? Yes, I did not reject that they're twigs. I still believe that they're twigs. I failed to reject the null. The null is false and I failed to reject it. So I went over an area that I thought was just a bunch of downed wood and there were snakes underneath it. I mean, I just thought it was nothing to worry about, but nothing at all, and I was wrong. So my type 2 error was the false negative because there were snakes there. So also a way to memorize this, and like we try to come up with these ways of memorizing. When you think about a type 1 error, you say A for alpha and B for beta for type 2. Type 1 is a false positive, type 2 is a false negative. It does depend on the context you're talking about, because someone could flip them around, but usually type 1 being false positive, where you think something is a snake but it's not. Type 2 being false negative, where you think it's not a snake and it is. We make these errors, they just happen to occur, and this is your alpha and your beta respectively, alpha and beta. So alpha is literally type 1 error and beta is literally type 2 error. The complement of beta for 5,000 points is what? The complement of beta is known as what statistical term? So we think it's a twig. So this one was, you think it's a snake, but it's not. It's a false positive. The complement of beta, 1 minus beta is power. Great job right there. And great question, Caroline, right there. 1 minus beta is power. That is the ability to correctly reject the false null is power. You can use hoverboards on water. You need power. Kind llama, fuzzy dove, lucky hair, helpful pony, and glowing dingo. Next question, here we go. Story time. You make a type 2 error. You believe the tree is healthy is the null. So remember, be careful. In a type 2 error, the null is false. So you should start thinking something right there, and you fail to reject it. And there's hints. It's a little bit easier, but think you should look at that null and be like, that is false, but I didn't reject it. Does everyone get it a little bit better now, I hope? Because you want to think, in a type 2 error, the null is false and you fail to reject it. So when you say the null is false, what are we saying? The null is that the tree is healthy. If you say the null is false, what are you saying? The null is that the tree is healthy. So in a type 2 error, the null is false. And we failed to reject it. Savannah said right there, the tree is not healthy. I mean, if the tree is not healthy, you should probably chop it down, right? But you fail to reject the null. What does it mean to fail to reject the null? You would think what? If you fail to reject the null, you would think what? I think Caroline's on the right track. because you don't reject the null. In a type 2 error, the null is false and we failed to reject it. Well, we got everyone answered. And then the picture kind of gives it away a little bit. So the null is false. It's not healthy. That's a false null. So you think people make these mistakes in real life where they're looking at a tree in their yard and they're like, should I chop down that tree? I kind of like that tree. I don't know. It looks good enough. It looks good. And then storm comes from last week, and then you're like, oh, now I got a tree on my house because I guess that tree wasn't healthy enough to withstand the storm. So people will ask me all the time, why would you make errors? And it's like, because you do, because you think the tree's healthy and it's not, and you just make errors. That's what happens. You make type 1 errors. What would a type 1 error be? Oh no, Amy, 5,000 points. So sorry to hear for your parents. A lot of people err on the side of a type 1 error there, because what would be a type 1 error? You should be able to hear me. Yep. I think it's just you. Exactly. A type 1 error is a false positive. Like you're like, I got to chop this tree down because I think it's going to die. You cut down a healthy tree. That's a type 1 error. Because if the null is the tree is healthy, the null is true in a type 1 error. The tree was healthy. So which of those errors would you never find out that you were wrong on? I guess you could kind of find out on this, but you definitely know on the other error. Like, you probably wouldn't figure out on the type 1, because you cut down the tree and be like, well, it looks, I don't know, look at the roots here. I don't know, the roots are probably bad. And they pay someone to do the roots, because that's harder than chopping down a tree. Like, I don't want to grind up the, I don't pay someone to do my roots. Expensive. So, teeth and trees, pay for people to do your roots. Never do your own root canal. Kind llama, fuzzy dove, lucky hair, helpful pony, glowing dingo. Next question, here we go. When doing a 2-sample t-test, the variables will be what? This one tricks people all the time. We've seen a lot of these today, so think about the examples we've seen. Put one of the examples in the chat, and if you remember the example, you'll know the 2-sample t actually requires this. A lot of people, because they know what the t is for, think it's something else. This is why I put this one in here. When you say QQ, what do you think about? When you say QQ, what do you think about? Anything associated with QQ? Anything associated with QQ straight enough? No outliers, pocket doesn't thicken? Any things associated with that? Ah, there's a fight in the chat right now. Regression. Regression is for scatter plots. Regression is based on correlation, linear regression. And a lot of people think it's 2 quantitative variables. The 2-sample t-test compares the what in the whats between 2 whats. Finish my sentence right here. The 2-sample t-test compares the what between the whats for 2 whats. The 2-sample t-test compares the what between the whats for 2 whats. Basically, I have it right here. The 2-sample t-test. Why'd you change your mind like that? Compares the difference in means between 2 groups. Great job, Aiden, right there. Compares the difference in the means between 2 groups. So you have to have 2 groups right there for the 2-sample t-test. Please check out these videos, the review list right here, review 3. You'll see me do each one of the tests. I highly suggest writing it down and working through it. The 2-sample t-test right there, and the chi-squared will be for 2 categorical variables. The chi-squared for 2 categorical variables. 2 more questions to go, but first leaderboard, kind llama, fuzzy dove, lucky hair, helpful pony, and lovely shark. 3 more questions. When working with statistical power, which of the following do we have the most control over? There are 3 things that go into statistical power. A lot of them we do not control directly. Which of the following do we have the most control over? And I think there's 2 right answers. If it's comparing the difference in means, wouldn't that be QQ? No, that would, and there is kind of a technicality to that, Mally, because, and I'm going to talk about this one next, because regression looks at the mean of the line across different values of conditional x's, the mean of y given certain x's. So kind of. But if you're comparing the difference in mean of 2 groups, that specifically will always be a 2-sample t-test where you have like males, females, and compares their GPAs. But technically, due to the way regression is done, Mally, you are technically correct. It would just be over multiple x's. The line is meant to be the mean of the x, which is why we have the linearity condition. That actually is the reason for linearity. I could get into the theory on it. I'm gonna go on, but Mally, really good 5,000 point answer right there, a question. I really like that because you're technically correct. But the difference between two means is a cat quant combination, males, females, GPA on the y-axis. So the three things that go into power are what? This is something you should memorize. The three things that go into power are what? You should have an example of each. What are the three things? They are on the screen right here, and then type 2 errors on the screen. What are the three things that go into power? One of these doesn't exactly go into power, but it is used to find power. Sample size, effect size, and alpha. Those are the three things. So sample size is the easiest one to control. It's how much data you collect. A lot of times people don't collect more data because it costs more money or takes more time. But you can easily manipulate your sample size, and that's not a bad thing to do. Your test will become more powerful. Power is the ability to find results. Textbook definition of power is the ability to correctly reject the false null. Power is the ability to correctly reject the false null. You Google it, that's what it'll say. Power is basically the ability to find results when results exist, reject the false null. So if you get a bigger sample, you can find results easier. If you increase your alpha, alpha is the point at which you what the null. So now we're talking about alpha. Alpha is the point at which you what the null. Like when you set your alpha, anything below that you will what? It's your significance level. So alpha is the point at which you what? Like anything below alpha, you reject the null. So if you increase your alpha, you can reject the null more because you have a higher level of alpha and p-values will be below it more often. So increasing alpha makes it easier to reject the null, but that's kind of bad because you're going to make more whats. Increasing alpha will make a test more powerful, but you will make more what? Provide an explanation of changing your alpha level, increase it from 0.05 to 0.10. Your test is more powerful, but now you make more type 1 errors. Dominic, great answer right there. Now you make more type 1 errors because you have a higher alpha level. And type 2 error is not directly controlled by these. 1 minus type 2 error is going to be power. So the formula for power is 1 minus beta. And effect size is the true difference between the null and the truth. Imagine there was a magical pill. And if you're working out, this magical pill, literally you put on 20 pounds of muscle overnight. Would that be easy to tell? Someone says, like, don't take magical pills. There's no magical pill. Someone says, if you take this magical pill, you're going to put on 20 pounds of muscle overnight. Now maybe we're not talking to an Arnold here, but maybe you're at like 140 right now and you're like, man, I want to take the magical pill. And please don't take them. But that would have a big effect, right? Now, there are things like protein powder, creatine, things that are perfectly legal to take. They don't have as big of an effect. It would be harder to figure it out. The test is less powerful because the effect size between the magical pill that magically puts muscle on you and the effect size of creatine and protein powder, which are good for you and take them in moderation and correctly, are not as strong. So which one, if the magical pill works and the creatine and protein powder work, which of those would be easier to figure out work? The magical pill puts 20 pounds of muscle on you overnight, and creatine and protein powder work the way that we know in the natural world that they work. So which of those would be easier to reject the null and say this has an effect? The magic pill, because it has a bigger effect size. The effect size is the actual difference you're observing between the null and the truth. The null is that it puts no muscle on you, like average increase of muscle for the person who takes it is 0. The alternative is it increases your muscle mass, and you would have much stronger evidence for the magical pill and easier to reject the null due to the bigger effect it has. Versus creatine, protein powder overnight, you might put on like 1/100th of a pound of muscle like every night, like very small. And of course, age and how much you've been working out, there's so many factors, so many lurking variables. Next question right here. Kind llama, fuzzy dove, helpful pony, lucky hair, glowing dingo. Next question. Calculate degrees of freedom between this right here. We have freshman, sophomore, junior, senior, and owning a bunny, yes and no. So what are the degrees of freedom for this test with that cute little bunny right there? Oh, it's a baby bunny. I'll tell you a bunny fact. So this is the chi-squared test of independence. We have a 4 variable question, and a 2 variable question. So you should, if you know how to do it, and I'll tell you how to do it in a second. Let me give you 3 bunny facts. Bunny fact number 1. If you ever get the chance to pet a bunny or pet someone's bunny, where do you pet a bunny? 5,000 points. Where do you pet a bunny? Where do you pet a bunny? Bunny fact number 1. You get a chance to pet a bunny. What do? Where do you pet the bunny? You'd be shocked how many people pet in the wrong spot. I would say between the ears is a good spot. Actually, do not pet its butt. And that's what people do by accident. And so we usually have to tell people when they pet our bunnies, don't pet its backside because they're prey animals. Since bunnies are prey animals, going behind them and petting them, they're just like, what's going on? So you usually go right here to its head and you pet its head and it'll kind of like press against you a lot of times. I literally just hold my hand out and Maury will just go into my hand, just like snuggling into my hand. So pet their heads, pet around their ears. That's where you pet bunnies. That's your random bunny fact of the day. I only had time for one bunny fact, as a lot of people got this. This was a 4x2, decreased by 1. 3 times 1 is 3. 3 degrees of freedom right there. Pet bunnies on the head or their shoulders. I like that too. Bunnies are fluffy. Good bunny. Next question, here we go. Kind llama, fuzzy dove, helpful pony, lucky hair, and glowing dingo. 2 more questions, I think. Oh, last one. How could someone make this test more powerful right here? So here we go. What could they do? There's only, I think, one answer that works. And yes, there is one answer that would make it more powerful, but you really don't do that. We have 2 bunnies, Jolly and Morty. They were in the intros today. Well, Morty was. I gotta get some video of Jolly. D-G-A-L-I, Jolly. Named after the Hunchback of Notre Dame, the goat in the film, because he likes to jump on our backs. If you lay down with Jolly, he'll jump on your like shoulders and he'll just like walk across you. So we're like, he's like a little mountain goat. And they're like, oh, I'm not going from the back of Notre Dame. So we named him Jolly. And then Morty after Rick and Morty. We're all like, Morty, Morty, Morty. He's a little. But Morty and Jolly. So, and his technical name, I think he has another middle name, but it's Morty Jan Michael Vincent. I always need another Jan Michael Vincent. But Morty Jan Michael Vincent. And I rarely have to say his full name. I don't know. He did some stuff right before we left. I was almost about to be like, Morty Jan Michael Vincent, what are you doing, you little bunny? Stop knocking over your little box. Just be a good bunny. Okay, right here to review as we finish up and have a little bit of fun. Increasing the sample size. And I do want to draw one last thing out. We're going to check out the leaderboard here in a second. Please check out the review videos where I do a lot of these right here. And did I lose my pen? I feel like I did. I did. Okay. The last review right here is when it comes to power. Write these down. If you increase sample size, if you increase alpha, or you increase effect size, you will decrease beta. And since you're decreasing beta, that would increase power, because power is 1 minus beta right there. And so beta is your literal type 2 error, and power is the complement of beta. And there you go. So that's sample size up there in the top. N is sample size. Alpha, exactly, Bryn. Type 1 error, effect size, which is the true difference between the null and the truth. And then type 2 error is beta, and power is 1 minus beta. Notice how these all right here are positively associated with power, but you really only control sample size and alpha. You don't control the difference between the null and the truth, which is effect size. They are negatively associated with type 2 error, and you don't control your type 2 error directly. It depends on how much you sample, what your type 1 error rate is, and the effect size. So it's time for the leaderboard, and everybody's favorite guest right here. You know him, you love him. It is gonna be, where is he?
I'm back. I'm Tiny Brian. I said there'd be special guests. Leaderboard time. We got Kind Llama in the lead. We got Fuzzy Dove and Helpful Pony. Make sure to email Brian. What's going on?
Go away, Tiny Brian. U-Bot is back. Thank you so much, everybody. Savannah, you are right. Kind Llama has won, and U-Bot is here to announce it. Also, Fuzzy Dove. Also, Helpful Pony. Email Brian right away. Brian, you do a very bad impression of me. U-Bot, out.
I thought I did a good impression of U-Bot. I really thought I did. U-Bot was not happy about that impression.
I see, U-Bot. I'll still do impressions of you. That's what I get. Maybe I'll do U-Bot 2 impression.
I like this U-Bot.
Which one's better? U-Bot 1?
U-Bot 2. U-Bot
1? U-Bot 2.
U-Bot 3.
Definitely not U-Bot 3. It is, yeah. MeBot 2 is better. Okay, we gotta remember MeBot 2. Let me highlight that. I'm gonna highlight that on the not soundboard. On the not soundboard, highlighting it. Oh, that looks horrible, but I'll remember now. On the not soundboard, totally not a soundboard. If you want to see it, the not soundboard, then we're gonna start 320. That's the Stream Deck. Where's my not soundboard? There it is, right there. There's the not soundboard. Right there.
There we go. There we go.
That's how all that's done, especially with the different sound effects over there. So good stuff. Thank you, everybody. Great job. Be reviewing. Be reviewing. This is not an easy test. It's not an impossible test, but it will catch you by surprise. So you're welcome. Thank you, everybody. We're going to start up the 320 review here in a second. I've got some chill music for myself. You're welcome, Katie. We'll see. Make sure to email me. I'll send out those Amazon gift cards. You're welcome. This keeps destroying my shirt. Lillian, great job. Congratulations. You're welcome, Emma. And thank you, Emma and Autumn. Keep reviewing. I feel like we had a great review right here, but watch the videos, watch the questions, know how to solve them. Any of these ones I did right here, just pause the video, try to solve them, see if you know the answers, and take notes. That's what we do right there. Okay, getting the review up and going. Let me go get that review. Are there any other practice problems we can do? The practice exam is great. Look over our old Canvas contents and any of the videos on the YouTube channel. I might have other videos where I've done practice exams. So if you literally go to the channel, I'll show you this right here. If I was a student, knowing what I know about this, you could go here. Exam 3 review extravaganza, huh? I used that name of a review before. So I did a 3-hour review here. It was only Stat 201. And look right here. Look at this. Type 1, Type 2 error review. Power review.
If the null is
So you got different things 1 year ago.
The person is actually
So these are different concepts from a different Brian with a microphone that actually spoken to.
If the null is false
So,
here, they're
good
actually
video right here. I'll
sick.
drop it in the chat. Then we're gonna start
So
with 320.
I want you to think.
There's this video right here.
In the words of a doctor,
But you can see it's all time stamped.
a
We just did it here,
powerful
so
test
I guess I'll time
would
stamp
help
this.
you determine for the T
sort of same
ratio right
examples.
here.
There's, you can tell
The
showing
difference right
relationships
here
with
is
the
literally
p-values.
y bar
Looks like
1
Canvas
minus
content.
y
Test
bar.
always
So
looks
that's what
like
I mean
Canvas
by
content.
difference. The standard
9.
How
So
are you
then
finding
margin of
to
error is
estimate the
confistrals, output, showing
some I'm raising
equations,
the
and
chat.
then
3, I
Kahoot.
need some I'm raising the chat.
Change the Kahoot up a little bit. Review in class 7 years ago. I remember this. I'm wearing my World's Fair shirt. I thought I was.
Add variable. Does this all make
Maybe
sense
not.
right here?
I don't know if I'd
Do
watch
not
this one.
cheat. What are we going to do to that in a type 1 error?
Wow. This is when I was doing I was also streaming online. Or I was, yeah. But yeah, in class. This is the full exam review right here. Is that 9 years ago?
So the first part right here,
Wait, what?
a random sample, and I'd like to outline, this is very important, a random sample right there to start.
What is this?
From Stat 201, the semester contains 65 students who got a C or better.
Am I talking on this?
Have means.
I might be talking now. I don't remember uploading this. I'll have to go look at that sometime. Well, okay, let's go back to the main screen. Okay, 320. It is hot in the office. I'm gonna try to make it up since 3 a.m. Who here is in the 320? Might get winners pretty quickly. Who's my 320s? 320, are you here? Can you hear me? Kahoot.com. I guess I saw Dominique here. Jim is here. Good to see you here, Jim. Abigail's here. Good to see you here, Abigail. Jaden saw you in the chat. Ethan, good to see you here. Allison, good to see you here. I'm loading up the 320 review. And I'm also going to load up the test a little bit here in the background. Not going to read directly off of it. Sheena, good to see you there. Mason, good to see you there. Major, good to see you there. Where's Ben? Where is everyone? I can see Sheena there. Over there. Where's Miles? Brendan, good to see you there. Look over there at that side of the class. And then Allison, right there. I miss, it's kind of, I don't know, I miss seeing people in person already. It's, thank you guys, gals, so much. It's really been a great semester. Like, 320 is not an easy class. 320 is not an easy class. Like, do not think for 1 second that you took an easy class. It's a lot of work. You're learning how to code. And let me put this in the notes here for this video. This is the video we're currently on right now. I don't even know what time. Oh, here we go. Oh man, this stream's already gone for an hour 30 minutes. So BAS 320 review. This, yeah, the toughest stuff is the exams. Yeah, I know, right? This is a challenging exam and a half. This exam, and I'm getting loaded in right here. I have the Kahoot, but I want to make sure I look over looking at the test a little bit here. And give you tips. Here. I've been up, so if I'm a little bit out of it, I got up at 3 on Wednesday. I got up at 3:30. Okay, every day is 3:30 because I got up at 3:30 on Wednesday. I got up at 3:30 on Saturday, and I got up at 3:30 today. I got to wish my mom a happy Mother's Day though, because I was seeing her in Virginia, and then she drove me to the airport, and my wife. And then I almost couldn't find my wallet because I put it on a. Hey, Ellie, good to see you there. You're welcome. I put my wallet on a window seal, and I just put it in the room we were staying in, the guest room. And then this morning I was like, I don't have my wallet. And then I was like, I can't fly without a wallet because I don't have my ID. And luckily we found the wallet. So found the wallet. My wife found it because she was like, Brian does this. He puts things on window seals. And yeah, it was behind the curtains actually. Oh, that's why. Because we went upstairs and I put my wallet on the window seal, and then we noticed the curtains were open, so we closed the curtains. And then I never saw my wallet again because I just had it behind the window seal. And you know, in the last 4 or 5 days, we've gotten up at 3 a.m. over half the days. There was 2 days we didn't get up at 3 a.m. and 3 days we did get up at 3 a.m. So yeah, it's a lot. Okay, let me give you some warnings here. This is not an easy exam. This is not an easy exam. The Kahoot, I definitely want to be, it's hard to make a Kahoot at the level of difficulty. There is some coding. When you start the exam, you will be presented with a file. I think I can show this here to start. Let me grab this. Here we go. I'm going to show you what you are presented with when you start the exam. Here is what you're presented with when you start the exam. Rules. Closed books, notes, internet, AI tools like ChatGPT. No communication with anyone besides your instructor. So if you have a problem, please get a hold of me immediately. You can have RStudio open and your notes, your page of notes. Now, to me, and I mean this means you can have RStudio open. So RStudio, and it's best probably have one thing of notes and using Control F in RStudio, but having RStudio open is just having RStudio open. Does that make sense to everybody? You can have RStudio open. So have RStudio open, compose your notes. You can put as much as you want in there. You can put everything from all your assignments, everything. This exam is really going to come down to your preparation, and I would use Control F. What I'd be doing if I was you is I would probably be using a lot of ChatGPT, having it explain things to me, but you have to know how to answer things. Once again, really hard to take big ideas and distill them into a Kahoot. I am Abigail, so I'm saying this straight up for my students. I'm fine with you having different pages because to me, you could just put it all on one page. So to me, it's just RStudio. You cannot use ChatGPT. You cannot use AI tools. You cannot use like physical notes. So we don't want to see you looking down at a sheet of paper or anything. And the screen record is on, so just make sure you're not doing anything crazy because if all of a sudden I have to go look at videos, it's like, no books open. It's just like, what notes did you take? And this is the way it is out there. Like, if you can do this on your own and you have your notes, you're good. And AI just changes the rules a little bit because like, it's really just a crazy world where you could just take a lot of exams now and just put them into AI and they answer the questions. But you're not really of use to a company if all you are is just inputting AI answers. Like if you're just going, because then you also have no idea how to check it either. Like, I mean, I would say maybe we could give an exam like Imagine this. Imagine if we gave an exam. This is I'll end my rant here. But the exam is 100 questions, and you have to make a 100 on the exam, and you can use AI. It's a pass-fail. So we're like, oh yeah, you can use AI, but what would you have to be able to do for every AI answer? Just think about this conceptually, because if you ever use AI, you need to be able to do this. So what would you need to do if you were using AI? Prediction needs to be made. Yep, we can do something like that. Abigail, here in a second. You got it. When you're done, report the percentile. So if we give you a 100 question, you'd have to be able to check every answer, right? So AI just speeds things up, but if you have no idea what the answers are, all you're doing is just an AI inputter. And we don't want that from you when it comes to tests. We want to make sure you know it. And so that's why we can't have you use AI really for tests, because people say, well, if you use AI in assignments, why can't you use it on tests? It's like, well, we're not having the AI generate the whole assignment. You have to kind of find your data set, know how to analyze your data, know how to write the code. And you can use AI for a lot of it. And then we see if you actually understood what you were doing with the test. Like, okay, well, you got all this stuff from AI, but you know what you're doing? You know what that means? And that's the point of the test, is make sure you understand it. And then it's like, oh yeah, well then go and use AI in a job, go and do that. Because we want to make sure you have the knowledge. Okay. We are gonna do the Kahoot, and then we'll answer the questions. Are you ready? Let's start the Kahoot. And then Abigail, we will do that right here. So take a look. We have it on the screen. And I think, Abigail, are you that one right there? Example question 5. A prediction needs to be made for x1, x2, x3. Report the percentile. Let me go see. Prediction needs to be made. I think you're talking right here. Yep. Determine if a prediction requires extrapolation with extrapolation check. And that's key right there. So Abigail, extrapolation check, which I think we did this on the last day too. Extrapolation check is going to have what format? Can anyone in the chat right now tell us how to do extrapolation check? Like, what is the format of extrapolation check inside of it? So right before we get started right here, what is the format of extrapolation check? What is the format of extrapolation check? What is the format of it? You have to know the format of it. What is the format of extrapolation check? I'll show one last thing here. So think about that while we get started here. Great answer, Allison, right there. Allison has it verbatim, and I hope this doesn't crash us, because last time I loaded something, we crashed the whole stream. That's why we have a different stream going right here. So with this, Allison has pointed out, when we do extrapolation check, and we'll start the Kahoot here in a second, we'd have to have right here something like make a linear model predicting weight from GPA plus height from data equals, you know it, you love it, survey time is back, survey time. And extrapolation only works in the multivariate world. So I'm on my computer now. I don't got to reinstall libraries. Got all the libraries. And now we go right here and we run data frame, left arrow. I call it data frame. It's much easier. New data. No, sorry. Data.frame equals, and then we go GPA equals 1, 2, 3, 4. And then we go here, height equals concatenate 70, 71, 72, 73. There's the data frame, unexpected symbol. I put a dot instead of a comma. And yep, Abigail, that's right. And then we go here to extrapolation check, make sure it's turned on. Red class has to be on. We say use the model M to make predictions on new data equals DF. And there you go, there's the percentiles right there. Does that make sense? Definitely have a note and an example for every one of these. Does that make sense what you would need? So what I would do if I was you right here is I would go, and if I'm making my sheet, I would have this right here, and you could even put like hashtags in here, and I'm pretty sure it doesn't do it. Right here I would just have this, and then you literally have this right here. So this is what I would do. You can create an R markdown file, whatever you want. And if you create an R markdown file, That's where it's going to look a little bit nicer. 2 seconds, and we're going to start the Kahoot. I would probably create an R Markdown file. And so in your R Markdown file, I would take, there's the starter chunk, don't delete that. And so then you could take this right here, drop this right here, and then this needs to go on a chunk. So then go here and go add chunk, R chunk, and call this extrapolation. And there's that. And then you could spin through this right here. Example question 5, chunk extrapolation. You can also control F in your document now for like extrapolation, and you could find these things. Does that make sense? This is what I would do if I was you. This is probably, I hate to say this, this is probably the most helpful thing we're gonna do right here. Like if you organize all your notes like this and put everything in there such that you have a chunk where you're like, oh, here's an example, and you don't have to load the data. That's just data loaded for an example. Does this make sense to people? This is what I would have to be like, okay, so I have to make a data frame of the X's right here. So these are the X's because X's deal with, yep, nice job, Abigail, right there. The extrapolation deals with how far out we are on the X's. And then we use the model and we see for the new data if we are extrapolating. And then the return here is the percentile by which. So the one that would require the most extrapolation is data point number what? The one that requires the most extrapolation is data point number what? Which has a what, a GPA of what, and a height of what? The individual that would require the most extrapolation is the individual what that has a GPA and height of what? They would require the most, they're a pretty extreme extrapolation of our model. So that individual would be individual what? What would it be? Individual number what? No thoughts? Individual number 1. Individual number 1 requires the most extrapolation. If you were right at the mean of the data, your extrapolation would be a 0. So if you had a GPA of about 3.7, a height of about 68.7 inches, we should get the average GPA like that. Yeah, now we're getting closer. Oh, I went through it. Oh, wow, the average GPA is a lot lower than I thought. Yeah, so we're getting close to the average GPA. Because if I get right to it, we would, and height, not near the mean of the height anymore. Ooh, yeah. Yeah, so it's somewhere, I'm having too much fun with this. Ooh, last try. No. Sure. This is about the average person, a GPA of 3.11 and a height of 35 inches. 68.35 inches. And they would require the least, like you're not extrapolating at that point, you're at the center of the X's basically. And being at the center of the X's is not extrapolating. There's data in this area when you're far out on your X's. And I think these are really good questions. Let me show you this right here. When you look at this, you can see where you'd be extrapolating. So this is what extrapolation is. And why is this extrapolation? Oh. Why is this? I don't know. Why would this be the idea of extrapolation next to me right here? Why would this be the idea of extrapolating? Why would this deal with the idea of extrapolating? Why would this deal with the idea of extrapolating? Conceptually speaking, why is this? And you have to look at the model we made, and the answer is over here. And so why is this dealing with the idea of extrapolating? So think this over. Why is this dealing with the idea of extrapolating? Yes, and so Allison has it right there because this is the XX combination, and these are the eigenvectors right here. Like we talked about this a little bit in depth the first time we talked about it and mentioned how it deals with eigenvectors, and you can see there's a higher degree of dimensionality in this direction and a lower degree of dimensionality in that direction. So the eigenvectors are going to be stronger, the orthogonal plane on the height direction if you turn it into an orthogonal kind of matrix. And so the further out you go in this, the more you're extrapolating. So if you notice, it's easier to extrapolate on GPA, especially you'll reach outside the cloud going that way. And it's also not perfectly symmetric on either side of the cloud, but you will reach outside the density. And I wonder if we just put in a GPA of 5, if we'll just instantly be extrapolating, or because of the way it works, we won't. And whoops, I don't want to plot it again. I just want to see the extrapolation check. Oh, it's down here. We're pretty much just extremely extrapolating by this point. There it is right there. We've reached outside the cloud of the density of the data, as opposed to right here with 2. We have not reached completely outside the cloud of the data with 2, even though 2's, I think, no, it's not quite a little further away. But once again, Allison pointed out, and this is huge, this would be looking at extrapolation right here, because this is a plot of the x's. So this, I'm still zoomed in. This being a plot of the x's is, are we extrapolating? So which point, like, and here's where people run into a problem, and I'm thinking of questions if you can't tell. If we have, like, this is a trick, or anyone says anything. If the data has a relationship like this, sure, why not? Which of these points would require the most extrapolation? Which of these points, A, B, or C, would require the most extrapolation? And this isn't meant to trick you, because we shouldn't even be adding a line to this. Which of these points would require the most extrapolation? Extrapolation is when you deal with your x's and look for unusual combinations of the x's that do not follow the central trend of the x's on extrapolation. It would be C, you are correct. And you don't look for the linear relationship between the x's. You think about where is the what of the x's. This purple circle is meant to represent the what of the x's. This purple circle is meant, as best I can do it, to represent the what of the x's. That purple circle right there is meant to represent the what of the x's. The mean of the x's. So now you think about the dimensionality of it, and it's a little hard to do. We do try to make this a little bit obvious, but you start drawing this ellipse right here that goes further and further out, and you notice kind of where they're at. I might not have drawn it perfectly, didn't mean for that one to go kind of in that direction, but I do think the test answers are pretty obvious. It's just you have to know what you're looking for, that C is going to be further out in the dimensionality than B. Also, B has some data near it where C doesn't. Don't just look for that. Like, don't just put a point right there and be like, aha, or this one lands on one data point. That'd be at the end of the cloud of the density ellipse right there. So extrapolation deals only with your x's. Extrapolation is only with your x's. There's a lot of big concepts to know right there, like extrapolation deals only with your x's. So this right here. Well, let's start up the Kahoot. Sorry. Okay, we got the Kahoot going. We're starting here in 10 seconds. So kind of how much an outlier, but extrapolation is not about outliers. Extrapolation is about unusual combinations of the x's, where outliers are things that are far away from the line and their y values. So extrapolation has nothing really to do with outliers. It's unusual combinations of the x's, which might lead to something being an outlier, but extrapolation, well, it would just have to have a y value that does not follow what its x combinations would dictate. But extrapolation is the unusual combination of the x's, where outliers are things that do not follow the xy relationship and are far away from their prediction, i.e. they have a large residual. Well, remember, extrapolation is going to be unusual combination of your x's. Here we go in 5, 4, 3, 2, 1. Let's do it. Time for Kahoot. I think you guys can hear the music still. Yeah, you can hear the music. If someone wants to predict views on YouTube, what model would they use? If you want to predict the views on YouTube, what model would you use? If you want to predict the views on YouTube, what model would you use? What would you use? This will be recorded. You got it. Good answer. You'd use linear regression. When do we use linear regression? When do we use linear regression? When do we use linear regression? Who knows when we use linear regression? When do we use linear regression? Quantitative y variables of interest. Logistic regression is used for categorical y variables. And so when you look at a linear regression, where is the significance of a model? Where is the significance of a model? So if we go and look at a linear regression, where is the significance of a model? Like we have a linear regression already. So let me go here to, how have I not put my output down below? Oop. Where is the significance of a model? Categorical X's make indicator variables. So where is the significance of the model here? Where is the significance of the model? The p-value, this right here. Great job, Owen. The p-value is the significance of the model right there. And we have right here the r squared is the percent of variation y explained by the variation in x. This is the r squared after adjusted for how many variables are in the model. And the degrees of freedom are for calculation purposes. What is the residual standard error? The residual standard error is what? What is the residual standard error? What is the residual standard error? Trying to find a question. The typical miss the model makes. Now, one of these we interpret right here between r squared and r squared adjusted. Which of these do we interpret as the percent of variation in y explained by the variation in x? I'm literally trying to find stuff over here that makes sure this Kahoot, if you watch it, you will know answers. To say this in class, which one of those do we interpret as blank percent of the variation in y is explained by the variation in x, which is variation in y explained by the model? The multiple r squared, the multiple r squared. Why do we have adjusted r squared? What is the real point of adjusted r squared? What is, in great job, Sheena, right there, what is the real point of adjusted r squared? What is the real point of adjusted r squared? To compare models, because it's a fair comparison. Models that have more variables will have a higher r squared adjusted, a higher r squared, and they could have a lower r squared adjusted because r squared adjusted is going to penalize them for having more variables. Now you want these two values to be what? What do you want these two values to be? A good model should have values that are what? Or r squared and r squared adjusted. Close. Exactly. It's because, remember, this is a penalized r squared. So if they're very close, you don't have a big penalty. If they're a big difference apart, then you hit a big penalty and it's telling you don't use the model. R squared adjusted can also be negative because you can get a big penalty. With this in mind, which one of these will always be bigger unless it's technically 1? So there's the technical instance, but which of these r squared or r squared adjusted will always be bigger? I'm going to relate every question we do to something I see over here. Which of these will always be bigger? The multiple r squared will always be bigger. Great job, Owen. We got to make Owen. Why is Owen not a mod? Owen not a mod. Gotta make sure. Major? I don't recognize the name. Okay, let's do the next question. Good review, looking at output. Here we go. Leaderboard time. Diligent Panda, Cute Lobster, Melodic Finch, Flying Panther, and Friendly Sphinx. $20 Amazon gift card or Starbucks gift card for first, second, third. Make sure to email me. Tell me that you won. Here we go with the next question. What is the typical miss the model makes? I feel like you should get this really quickly and really easily. Go ahead and put down the typical miss the model makes. The typical miss the model makes. What is the typical miss the model makes? Okay, it's going to be the root mean squared error. So with this, let's take a look over here at another concept. What am I currently finding? What in the world are those? Wow. Is that good or bad? As a statistician, I see this and I say, wow. Is that good or bad? Wow. What did I find and what does this mean? What does that find and what does this mean? I'm gonna write another code while you tell me what this means. And I'll tell you the answer to the code here in a moment. It's good. Why is it good? Mubot said good morning because you said good. Variance inflation factor, they're good because there's next to no multicollinearity. Now, the only way there can be in low redundancy, good answers in the chat is yeah. These are all great answers. What is the lowest variance inflation factor can be? The absolute lowest variance inflation factor can be is what? What is the absolute lowest variance inflation factor? Can be 1. Great. Oh, and man, we'll throw you 5,000 points if anyone's here to get those points. 1 minus 1 over r squared of the I in the model. And what's interesting, if you only have 2 x's in a model, it's technically collinearity, and they will always be equal because the relationship one x has with the other x will be the relationship that x has with the other x. So the r squared between these is going to be very close to what? Be super duper close to this. This is a model of an x with an x. Looking at the r squared sub I, the r squared sub GPA, because this is the r squared of an x. So variance inflation factor looks for the amount of shared overlap, multicollinearity between the x's, and it's measured on a scale of 1 to infinity, 1 being the lowest level of variance inflation something could have, and the r squared sub i's would have to be close to what? Think mathematically, to get 1 out of this formula, the r squared sub I would have to be close to what? Conceptually, the r squared sub I is going to have to be close to what to get 1 out of this formula? 0. And that means you really have no overlap between your x's. This is not a good r squared. It is the shared variation or redundancy among your x's. And so this would be bad right here. This is a bad thing. We don't want that. So if I look at the r squared here, look at that. The r squared is pretty close to 0. That's the adjusted, but the r squared is pretty close to 0. And if you take this right here and go 1 over 1 minus r squared, you get that number. And that number you see right there, oops, oh, because we have the other model. So that number you see right there is that number right here, just not enough decimals. So it's 1 over 1 minus r squared sub I. And you also look at the model dependent VIF, but if it's close to 1, it's like there's no redundancy. So what variance inflation does, and this is the key thing, and I really like having my PC so I can write and draw on the screen easily. Variance is actually what squared? Like if you break down variance inflation factor, variance is actually what? Variance is actually what? Like the idea of variance, it's on the screen now. Man, Allison's got all those answers. Yes, it's standard error squared. So the standard error squared, when you're finding the high cutoff, use the original right here. Yep, use the original r squared. Good question, Owen, right there. It's the standard error squared because standard deviation squared of variance. So this is actually standard error squared inflation factor. So if you had a variance inflation of 16, then that would mean your standard error is about how many times bigger now? About how many times bigger is your standard error if your variance is inflated? So you could do that right there. But the standard error inflation is about 4 times, which means you have about 4 times the uncertainty. And that means, think about what we have right here, and we'll do another question in a second. That means this value here is probably about 4 times bigger. Like you have 4 times the uncertainty because of that. That makes confidence intervals wider. It makes it harder to get significant p-values because you have more uncertainty in your estimate. Standard error of an estimate is the uncertainty in that estimate, and you don't want large standard errors. You would like standard errors to be small, which would lead to large t-statistics, which would lead to low p-values, meaning you have a statistically significant variable in your model. So large standard errors lead to more uncertainty. And variance inflation comes from the redundancy in the x's, and that's what VIF checks. It does not check conditions of the model. It does not check linearity, normality, anything like that. It doesn't look at the predictions to see how good the predictions are. That would just be residuals right there. It's just about multi-collinearity, redundancy, all that good jazz right there. Good stuff. Let's do the leaderboard. Cute lobster, diligent panda, melodic finch, friendly sphinx, and kind dog. Next question. What is the misclassification rate of this model? Ooh, I love this right here. Ooh, misclassification rate. What is the misclassification rate? Yeah, there it is. Yep, Nathaniel, good question right there, and I'll answer that here. I'll answer that right after this one, and I'll go into detail. So literature will tell you 5 or 10, like you can literally Google it, and it'll be like 5 or 10 is a high VIF. So what we do in this class, and I'll talk more about this one, is we create a model-dependent VIF, which Owen was talking about, where we use the VIF formula of 1 over 1 minus r squared. And let's say the model has an r squared of, let's say, 90%. This creates the model-dependent high VIF cutoff, and it would be 10. So why we use this is because when your model does really well, you would be more lenient on your x's stepping on each other's toes, because they explain 90% of the y. Well, maybe my x's are going to step more on each other's toes. And this kind of gets interesting if you think about it, because if this is the r squared of our model now, what is the model dependent VIF, which maybe some people in the literature are going to get mad about, but what would be the model dependent high VIF now via this formula, where this is the r squared right here of the model being input into the VIF formula, making a model dependent VIF of 100. So because our model does so well, we're allowing it to be more lenient, and we'd be like, well, if VIF's more than 100, we will allow it to pass. And VIFs do not invalidate a model. It just means you got a lot of redundancy in your x's, which are going to make it more confused about, which x's should go in the model and if they're statistically significant. It's really bad for descriptive models, not so much for predictive, where the predictions is the only thing that matters, because VIF deals with the x's, hence r squared sub I of the ith x. So a descriptive model gets hurt way more by VIFs because you're going to have more uncertainty in your coefficients. The one we just did right there, the misclassification rate, how did we do on the answers? Pretty decent. We have right here what is called the on diagonal. So the on diagonal is where what matches what and what matches what. The on diagonal is where what matches what and what matches what for this matrix. The on diagonal. The on diagonal. The on diagonal. Predictions and actual match right here. That's the on diagonal. So this is the yes, yes, no, no, exactly. And this is the on diagonal. So if you take the on diagonal and add the numbers up and divide by the total, what do you get? You get the what? And I know this is not what we're looking for, but I want to show this because, once again, it's not about answering one question. It's about knowing how to solve any question. You get the accuracy. Great job, Owen, right there. You get the accuracy of the model, and we shouldn't get decimals, so that's a problem. And why is having the accuracy so good for getting the misclassification? Why is having the accuracy so good for getting the misclassification? Which you could do the off diagonal then if you want. So why is the accuracy so good for misclassification? They're complements. Great job, Allison, right there. They're complements. So you could just solve this right here too and get the misclassification rate of the model. And there you go with about 12%. You can find exactly, but it'd be about 12%. And I would say that if I was in a meeting, I'd be like, well, we get about 82% classified correctly. And I will say this, the naive model over here is only seen in this portion. This is the naive, because the naive does not use the x's. It only uses the actuals. So when you have the naive model, the accuracy of the naive model would be what number over 13,594? That's where the naive model sits in the confusion matrix. So the accuracy of the naive model would be what? Yep, You're right on. Yep, because that's the majority class. So you'd predict everyone is no, and the accuracy of the naive model is 11,195 over 13,594, which is actually, uh-oh. Wait a minute. Look at this. I don't know if this is a good model now. Whoa. Oh, wait a minute. 8235. 8235. Oh, I subtracted? Did I? Oh, I subtracted. Okay, wait. 11094 plus 89. No way. Am I crazy? Or does our model do what? This is a bad model. No, I'm not crazy. Do you see it? This model's trash, unless we maybe get some false positive, false negative thing out of it. This model's pretty darn bad. This model has a lower accuracy than the naive model. It's actually worse than the naive model, unless I'm doing my math wrong. Our model is worse than the naive model by 1/100th of a point, which means if we just say everybody's no, we'd do just about as good. And so why are we doing models when we just say, just nobody does it? So yeah, you could look at the predicted yes then. I guess if you take everyone who's predicted yes, I don't know, you could get about half right, which I guess is better. If you just take all the predicted yes and then market to them, I guess that's what you'd probably do. You take all your predicted yes and market to those people, and you do better than random chance because there's only a 12% about yes, and then you would increase it from, yeah, so I guess you could use it that way. So you'd have a lot of type 1 errors right there, but yeah. So that's where the data needs context. We got to look at it and see if it's worth it, and we would get about 45% sales if we're trying to do sales there. So might have some use. Better than just picking a random person and having a 12% chance, but there you go. Okay, let's continue on to the next question. Diligent panda, cute lobster, melodic fish, kind dog, gentle wombat. Here we go. What does this output indicate? What does this output indicate? Ooh, I love it. What does this indicate? Trying to find. Make sure I speak very specific. There's one right there. Ooh, only a few people got it. Only a few people got it. I'm trying to find one right here that. So this is the output of a what right here? What is this the output of? What is the output of? Yeah, technically yes. It's the goodness of fit from what function? It's the goodness of fit from a what function? Found it in one spot. Check regression, exactly. This is also not a linear regression. This is the logistic regression. This is a check regression, logistic regression. So the null hypothesis for a check regression is what? So when you make, here we'll go check right here, and we'll run a check regression. We're not going to see the same output here because we're doing a check regression on a linear model. And now we get, is the linearity of GPA met? No. Is the linearity of height met? No. Is the linearity of our overall model good? No. Is the p-value or the equal spread good for our model? Yeah, it passes. Barely, but it passes. Is the normality of our residuals good? No. Now that our sample size is more than 25 for the linear model, we have to go and look at the plots. So we need to put on extra equals true right here. And we get the extra plots now. Here we go. Which of these looks to have more of a problem with linearity? GPA or height? Which of these looks to have more of a problem with linearity? GPA or height? Which of these looks to have more of a problem with linearity? GPA or height? These looks to have more of a problem with linearity. Height, definitely. It's got this swoosh right here, these points above the line. This has a little bit of unequal spread, but we look at the overall model for that, which somehow passes because the p-value above 0.05. Do remember the null hypothesis for any condition is good till we have evidence bad, evidence low p-value. And so we do have a problem here, the swooshy nature of it, which carries through to the overall plot. If you look at the overall plot of it, it does have that swoosh probably coming from the height variable. How do these residuals look on an A to F scale? There's an outlier, there's a minor outlier, there's a... Ooh. How do these residuals look on an A to F scale? No looky histogram. How do these residuals look on an A to F scale? Like, because we saw there was a problem with the normality of the residuals, which is this plot. The overall model is here, and that's pretty bad. The equal spread is here, and it passes. So, like, this is literally these plots. How does this look on an A to F scale? What do you think? 5,000 points if you get the same letter grade as I... Yes, I was actually thinking D. I was thinking I'd give anything for in the D range. I've seen worse. I don't know. It's pretty bad, and towards the middle it's good, but pretty bad. Major issues. D or C. I don't know. You can't say A or B on that. If you give that an A, I'd be like, oh my gosh. Does not follow the line at all. That's got some major problems right there, and good job. I am peeking over at the test, trying to make everything test relevant. So I'm trying to, between all these long pauses between questions, because there's only 16, I'm looking over here and giving you advice. I missed, what is the null again? The null for any check regression is that the condition is good. So if we are seeing if the logistic curve is a good fit, the null would be what? If we're looking at the logistic curve, the sigmoidal curve with these two tests, the null would be what? The null would be what? I mean, basically, that's the null. And since the p-value is high, you don't reject the null. The null would be that the sigmoidal curve is a good idea, and since we're doing a check regression right here, we would not reject the null. We would still believe, we do not have evidence that the model is a bad idea. So we would still believe the model is good. We do not reject the null. We do not have evidence. This model actually, now it might not be a good model, but the idea of fitting it is a good idea. Like the sigmoidal curve is a good fit to it. So imagine this, like if you're wondering what this means, imagine you are trying to fix a computer and the computer has a slot that looks like this right here. So here's the slot. And then you get a part that looks like this. I cannot draw the reverse image of this. You get a part that looks like this. Is this a good fit? Is this part right here a good fit? Is that a good fit? Yes or no? Is that a good fit? It's a good fit, as best as I can draw. So that means that you can do this. Now, does this mean that this part is working? Like this is a significant part and it's working? It just means it's a good fit. That's all we've established, is this a good fit. We don't know if it's we don't know if it's a good part. We just know that it fits. Like this is a thing we can do, or we should do. The check regression only goes to the idea of should we be making this model, not does the model work. That would be like things like the summary or confusion matrix to analyze the R squared, the typical miss, RMSE, or confusion matrix for the misclassification or accuracy rate. And those are the ideas of how good is this model. This does not speak, check regression does not speak to how good the model is. It only speaks to should we be making the model and are the assumptions met. So, and Nathaniel, good question right there. This is for check regression only. P-values higher than 0.05 mean that we do not have evidence of a problem for check regression, not for all p-values, only the check regression p-values. Be very careful because a lot of people say, oh, high p-value good, high p-value bad. It just means we do not reject the null. There's not evidence of an issue because the null hypothesis was that the conditions are met and we don't reject. Sigmoidal curve, good idea. Logistic regression. Diligent panda, cute lobster, melodic finch, kind dog, gentle wombat. Next question. How many assumptions do we fail? So watch out for the trick right here. How many assumptions do we fail? How many do we fail? very careful. How many assumptions do we fail? I think this is a little bit of a mean question. Sorry if you get it wrong, because technically this is a simple linear regression. That is the trick. This is such a mean question. Brian writing it. Such a mean question. Such a mean one. Oh, and I get both points. Woo! Woo! Such a mean one. So, bro, don't worry, you got it right. You fail a condition when the P... So check regression, you fail a condition when what? You fail a condition in a check regression, not just p-values in general, but when you're doing a check regression to check the assumptions, which the assumption is linearity is good, equal spread is good, normality is good. Then you have two friends who disagree, Nathan. Good question, Nathaniel. If you have one high p-value, one low p-value, it's kind of like... You just kind of look and you go, I don't know, maybe I should do this. They use other evaluation metrics. So how do you know if something has failed right here? Because that's scientific notation for 0.001. 0001, I missed it. Right there. How do you know if any of these are failed? How do you know if any of these are failed? Below 0.05. How do we get coefficients? How do we get coefficients? How in the world do we get a coefficient? If you had to find a coefficient, what code do you run to find coefficients? Like, what code do you run to find coefficients? Summary. So you have to know where to get a coefficient in your model. And so tell me this. First off, why is this code not going to work? Wait, don't. Why is this code going to get mad at me? Fix that code to start. Why is that code going to get mad? We could try it. There we go. That's what I wanted. Oh, you can't. Gosh, I'm zoomed in still. Sorry. 1,000 points. Why is that code over there going to get mad? Why is that code going to get mad? It did get mad. Why is that code mad? Yep. When you do logistic, GLM, and family binomial, you can always do a new line. And any of the binomials work. I'll try to make some Perta code right there, and now we get it. What is the coefficient of weight? You can type the first two decimals. I'd copy paste if you're putting something in online. Like if you have to put anything into R or anything, just or put it on your quiz, your test. 0.03. Yep. There's the coefficient of weight. What is the amount of uncertainty we have in weight? What is the amount of uncertainty we have in weight? Great job, Alyssa, right there, and Allison, and Sheena, and Owen. What is the amount of uncertainty we have in weight? Yep, the standard error. If you notice, you divide those, you get the t ratio, or the z score, sorry. Then the p-value, which these are all extreme except for GPA, which is not significant. So very, very good stuff right there. So make sure you know how to get coefficients. Coefficients are found by summary. You should know what all of these are, your coefficients. And you should know how to make predictions. You can also make predictions by storing a model right here, like data frame, store into data.frame, and go right here and do height equals 70. Here we'll do mine. 75 inches, weight equals 181, and GPA equals, I'm definitely male because, sorry men, we don't do well in the GPA. If you don't believe me, I'll run the associate function and show you the math. So, sorry, just data. And so we go right here, and I didn't help out, so I'm part of the problem if you can't tell. And we go here to predict, and I always forget this one. It's type equals response, I believe. And then data new equals data frame, and there we go. What does that mean? What does this mean? What does that value down there on the bottom mean? What is it? What is this? What in the world is that? Explain to me that. What is that? Kind of that. Kind of. Yep. And you could do an interval on this. You could do... You can get an interval on this. interval equals. We do it. Oh, you can't get intervals on that one. What do we do? Take off this. Wrong on this? Maybe it won't do it for that. Yeah, it's a bummer if it won't. That's fine. Ooh, what is this value? Be very careful. Allison is 100%. The first value was Brian has a 99.17% probability of being male. This value right here is not a probability. It is a what? That value is not a probability. That is a what? That is not a probability. That is a what? Starts with an L. Prediction. Logit. Logit. The logit is what you get when you solve the equation itself, and if you don't do type equals response, you will get the logit, which is the solve of the equation. If you go through and solve the equation mathematically, you get the logit. If you input it in to the e raised to over the 1 plus e raised to, you get the actual predicted value. So once again, know this formula. It is literally the formula of your regression equation of e raised to the regression equation b0 plus b1x, and more x's if you have them, over 1 minus e to the regression equation. And if there's more x's, you just add in the more x's, like plus b2x2. So good stuff. Good review. It's tough and there's a lot to keep straight. Even sometimes I have to think for a moment. Okay, let's do the next Kahoot question. Diligent panda, cute lobster, gentle wombat, melodic finch, and kind dog. Here we go. If we fail the test with p-values, we can't use the regression model. True or false? If we fail the test with the p-value, we cannot use the regression model. Fail it. Can we use it? I'm looking for more things to test you on. No, we can use it. Just bad thing. One thing we want to look at here, look at a few things. Once again, I'm always pulling up extra things to help out. So if you're skipping these, you're skipping some major stuff. We've got a lot of really important codes to use. So the important codes we have are things like drop one. What is drop one? What is the idea of drop one? Does anyone know as I write some code right here with the drop one? Let's go, Declan. Good to see you there. What is the idea of drop one? What is the idea of drop one? Survey 10 all the way. What is the idea of drop one? What is the idea of drop one? Drops one predictor from the model and looks at the overall impact of it. Now, drop one, great job there, Allison. Drop one does have a slight change to it depending if your model is what or your model is what. Drop one does have a small difference right here depending on if your model is what or your model is what, which I'm building another one of these. So drop one does have a difference. It depends. Multiplications for interactions. Logistic or linear. Logistic or linear. So this is a linear drop one with the F test, and this is a logistic drop one with the chi-squared. Notice how it's using the chi-squared over here to do the computation. Technically, I think you can still, oh, bad. Warning, and a little different. It gets mad. It says, don't do that. With this right here, the reason we don't look at the individual variables in a model is because they only tell you the significant difference from the what when they're indicator variables. When you have an indicator variable, which means it's categorical in nature, you only see their differences from the what. When you have indicator variables, you only notice their difference because we have right, left, and then we're missing one from the reference level. So while both of these are not statistically significantly different from the reference level, they might bring additional information as a variable as handedness, and the answer is that they don't. So drop one is a quick way to just drop variables from the model, and it'll take variables as a whole. What is the name of this variable? Look at this model and tell me the name of the variable. Be very careful, because there's indicator variables and then there's variables in a model. What is the name of the variable in the model? The name of the variable is what? Because there's indicator variables and then there's variables. What is the name of the variable in the model? The name of the variable. The name of the variable that went into the model. Handedness. Handedness then created indicator variables. So handedness is the variable creating handedness left and handedness right. Those are the indicator variables. So remember, to check the significance of categorical variables that have more than 2 levels, 3, 4, 5, you need to drop it from the model completely, which you're actually doing for 5,000 points, a what test. The drop one is actually a repetitive what test. The drop one is actually a repetitive what test because it just does it for each one. Some of them are not important, like we would know this is significant because it's just one variable. Partial F, great job, just right there, Allison. Partial F repeated, just doing it for each variable. It's just dropping one, looking at a model without it, looking at the significance, and doing it repetitively. And if the drop one comes back with significant, that means that that variable brought with it additional information. So you can see right here with this drop one, the handedness variable, I just ran it all, but the handedness variable does not bring new information, not accounted for already, does not help reduce the deviance from the null model right there. Okay, let's do another question. Here we go. Diligent panda, cute lobster, gentle wombat, kind dog, and tropical horse. Next question, let's do this. Which assumptions can be checked with a QQ plot? Look for another good one right here. What can we check with a QQ plot? Get this. Which of these can be checked with a QQ plot? And actually, if you know where to look, the QQ plot is right here. The QQ plot is used to check normality. The normality right there, the QQ plot. And great job on those answers. Really good work. Owen Wilson, wow, right there. How do we put, because I think Jaden was asking about this, how do we put in interactions in a model? How do we add in an interaction? I'm just going to keep clicking knit. How do we add in an interaction? Weird phrase. How do we add in an interaction? Didn't do it. We multiply. Whatever two variables we want an interaction on, we go right there and we multiply, and we have the interaction between the variables. You can actually, and don't do this, well, I think the exam's pretty clear. Don't do this, because if you do this, you only get the interaction. So if you do this, you only get the interaction right there, and because it's on an indicator, it looks that way. Make sure to do the multiply, and it carries through model hierarchy, which means you get the x1, x2. X1 plus x2 just puts the variables in by themselves, and you get x1 and x2. Comparing that, and that would be all the variables interacting with each other to the second interaction. It's all interactions, all two-way interactions. That's the phrase I was looking for. All two-way interactions, which makes a lot. And this is all three-way interactions, which is ridiculous, and we run out of degrees of freedom, so we can't estimate coefficients. I mentioned that briefly in the 201, but without degrees of freedom, you don't get coefficients, and that would be bad. So be very careful making your models crazy like this, and we probably get a horrible, we might have reached an r² of 1 actually. We did. And then it says, I cannot find you the r² adjusted because it'd be 1 anyways, and that's just conceptually a bad idea. So that would be a saturated model with way too much in it. Good question, Joseph, right there. But that would be all variables with their two-way interaction, which Joseph wrote, dot second power, dot raised to second. All variables, dot second power raised to their two-way interactions, brought to their two-way interactions. And so technically what you could do, you could take these variables right here. I wouldn't write it this way. Does everyone see the similarity right there? Whoops, of course I make an error. If you notice this, we're just putting them in a little mathematical parentheses and then raising it to the second power to show that if you just take the two variables and raise to the second power, you get the interaction between them with the output right there. So the interaction term has a coefficient of what? What is the coefficient of the interaction term? What is the coefficient of the interaction term? It is negative 0.41. And right here, I really like this. So if you were to tell me, what is the equation for females? This is correct, Alyssa. We can change that, but in logistic, the level of interest is last. What is the equation for females? Which is the reference equation or reference line if you're doing implicit lines. So what you do, you want to write the equation for females, is you take the output, you simply put in zeros for males. Really great questions, everyone. I think that's it, right, Owen? You just go right here and you say, well, males go away, and that goes away. And more specifically, there's the equation 64.45 plus GPA times 0.12. So exactly Owen right there. And then what you'll notice is if we're predicting for males, then what you do here is you'd put a 1 for male, and you'd put a 1 for male right here. So just round the numbers. I'm going to make it easier. Rounding the numbers, what is the male intercept now? Positive, right? Or I don't care. Rounding the numbers, what is the male intercept? Is it negative? No, it wasn't negative. Rounding the numbers, what is the male intercept? So the male intercept, that indicator changes the intercept by that amount. The male intercept is what? Exactly, Alyssa, yep. And then the male slope is what? Just estimate the male slope for me. What is the male slope? What is the male slope? Just use those numbers, they're easy to do. Like I can do those in my head now. Because then you combine like terms. So think about how this is a like term like there, because it's all plus. It's this plus this plus this plus this plus this. Negative 0.28, exactly. And I think once you realize you're just putting in ones and zeros, which are the values indicators tend to take on, then you're just like, oh, the female slope is like this, the male slope is lower. And if we go visualize this, that's what we should see. We should see males have a higher intercept at 72 something, and females have a positive slope where males have a negative slope. So if we visualize this, and there it is. Oh, I've got some sort of, I always forget this one. Oh, it's power and flow. Parameters, M flow. I remember this off the top of my head. No! What is the thing? Someone tell me in the chat. Just forget this. M flow. What? Did I do it? Oh my gosh. I stand for like rows. I don't know. But I got it fixed. It's the parameters of the plot window, and you fix it by making it a 1 by 1. If you really quickly right here, I'll show you. If you do something like 2 by 2, then you do this, and you can make. Oh, now I lost it. But it's the parameter window that changes it. So good stuff. Okay, so we've talked about the implicit lines and how to write them. Next, leaderboard, diligent panda, cute lobster, gentle walnut, kind dog, and flying panther. Which level has the strongest relationship? Go ahead and tell me right here, which level has the strongest relationship? Pretty easy to see if you know what strongest means by this. The The strongest means steepest. And it could be negative, it could be positive. Everyone got that. I like that. Wow, nice job right there. So, Mr. Pickle Sandwich is here? Oh no, it's the level. Oh, look, Mr. Pickle Sandwich is here. He's in 201. And let's take a look at this model back here. Let me go look at a different model. Man, my brain is... Your brain on 3 hours of sleep. Like, okay, here we go. Let me make this a 2 variable model. Oh, now I need... What? Okay, good. Whoa. Which one has the strong... Just type a few letters. You don't got to type the full thing. Which of these has the strongest relationship? It's probably due to lack of data. And it's trying to fit for only like 3 points. Hence why the curve looks like that, because it doesn't have enough points to draw a smooth curve. Or no, it's just a... ambidextrous is just like, man, once you hit 67 inches, you just 66 inches female, 67 inches male. Apparently that's the way it goes. I didn't know this about the world. But when you look at this right here, you actually have to think about how you'd make predictions with it. If you are predicting down here, who would have the highest probability of being male? For a 65-inch person, the person with the highest probability of being male would be what? So clearly we can see the strongest relationship is ambidextrous. There's some lack of data issues stuff. But the person with the highest probability would be what? At 65 inches. Left-handed, exactly. You just look at where the curve is at, and they'd have the highest probability of being the level of interest. And once again, the level of interest is last in logistic. So we would say right here, the person with the highest probability of being male is going to be the person, if at 65 inches, would be the person who is up here highest on the graphic. So the logistic always predicts the level of interest of the variable we're looking at. You always get probabilities between 0 and 1, hence the sigmoidal curve. Okay, next question. Diligent Panda, great job. Cute Lobster, Gentle Wombat, Kind Dog, Tropical Horse. Here we go. Multicollinearity is measured how? How do we get that multicollinearity with some, ooh, GG range right there. So multicollinearity. Level of interest is always last alphabetical. The way we do it, that is correct. That is correct for the way we do it right there. Multicollinearity. A lot of things to say about multicollinearity that we've been talking about. It's going to impact the standard errors. It's highly correlation among the x's. And yeah. And so right here, you can see it does not invalidate the model. It's shared validation or shared variation. Has nothing to do with the y's. Nothing to do with the y's. And doesn't impact the predicted power of the model. It's going to be the shared variation among the x's. So with this right here, I'm trying to find another good question. Yeah, okay. Let's check this out. One of my favorite questions of all times. Made a billion questions on this. We can do it on this one. Here we go. What in the world am I trying to figure out right now? What is this? What is the point of this? What are we trying to do? What is the point of this? What are we trying to do? Yep. Which polynomial model is the best fit? So here's the steps and write them down. Step 1 is what? I want you to kind of remember two right now. Step 1 is what? Step 1 is what? What is the first step of looking at this output? Step 1 is what? First step, you do what? Find the highest R-squared adjusted. Boom. There you go. How many models could possibly be the answer now? Because of this, how many models could possibly be the answer? Because that is the highest R-squared adjusted. How many models could possibly be the answer? How many models could possibly be the answer? Close. 3, Any model at or below that. Close. 3. Any model at or below that, because that's as high as we can go. We're not going to go above it because it's the best. Why would we make it more complicated if it's the best? So now you take the best and you subtract what off of it. Now be careful. It's kind of like statistical significance, but not, because we're kind of like, well, I mean, if something's really close to it, we're okay with it. So we take it and we subtract point, and great job, 0.005 off of it, and there we go. Now you simply look and you start at the bottom, and you go, is this as good as that? Does this meet the criteria of what we want? Yes or no? Just say yes or no in the chat. Is this as good as this? Is this as good as this? Nope. Is this as good as this? Like, it has to be as good or better. Is this as good? Yeah, that meets it. And what you can do is you can go to max order 2 and you can kind of look at it and see how it changed up. If you notice, it's kind of picking up on the bend here at the end. That's probably what it's trying to, or how it's doing better. And I don't think it's too overfit. I mean, we went from a 1.7% R squared to a 3.6% R squared adjusted. Thank you so much, Major and Jaden. Good question, and Major answering right away. You got it. Good answers. The max R squared adjusted. Subtract 0.005 off of step 1. Find the highest R squared adjusted. Step 2, subtract 0.005 off the max R squared adjusted. Step 3, start from the bottom and find the first one that meets the criteria of having that criteria we found right here. Criteria. Woo! I'm gonna sleep a lot tonight. Sleep good. I was given advice on life, and I said sleep, eat, and move. There you go. That's all you gotta do. Cute lobster looking like a bunny. That's why you're winning. Diligent panda if on fire. Gentle wombat, kind dog, and tropical horse. Yep, subtract. We picked the lowest order above. Correct. And that's why, Alyssa, we start at the very bottom of it. So you start at the very bottom and you go, is this higher than it? No. Is this higher than it? Yes. Order number 2. So after you find out the threshold, step 2 finds the threshold. You start at the very bottom and you say, is this higher than this? No, because it's not. 0.017 is not higher. Extra credit on what? Tell me what I said, Major. I don't know what I said. And this is higher than it, so that does meet the criteria. Tell me what I said, because I don't know what I said. You'll have to remind me. Next, extra credit on the bunny, maybe? Next question, let's do it. What do the VIFs indicate? It popped up EC. Oh, it popped up EC. Oh, sorry, I don't know. Another good set of VIFs right here. I'm gonna go find another thing, so I want to make sure. I think the Kahoot's okay, but I'm finding a lot of things. Oh, yeah. Oh, I love this question. I love this question. Okay, I found one that I'm going to replicate. So I'm always trying to think of the concepts that are on this and like replicating and basically trying to make sure you understand. So why do indicator variables exist? Why do indicator variables exist? Indicator variables exist, why? And how many indicator variables could be made from this data set? Why do indicator variables exist? Why do indicator variables exist? Indicator variables are created from what's. We can't make 19. Good guess, Evan, right there. We can't make 19 indicators from this. Indicators are only made from what's. Indicator variables are only made from what's. Categorical X's, cats, all the cats in the chat right there from Ubot. And so if you look at this data set, how many variables introduced into a model would create indicator variables if they were the variables selected? How many variables, if we introduce them into a model, would create indicator variables? How many variables here would create indicator variables if we introduce them into a model? Yep. And so you go right here, if gender is an X in the model, if handedness is an X in the model, and you know what's really neat is you can also tell how many indicators they will make. So when we make indicators, there's always a what level. If you make an indicator, there's always a what level first. Indicators always have a what level. Indicators always have a what level? A reference level. So what you have is you have L-1 levels. So there'd be one indicator over here, and then right there, there's the two indicators there. I have that slightly off the screen, L-1. And then there's the one indicator there. And that means the first one alphabetical, and thank you, the output, for putting it first alphabetical, is the reference. Female's the reference, ambidextrous is the reference, and no is the reference. So there's always one reference. And then why does handedness have two indicators? We've seen that earlier today. Why does handedness have two indicators? Because there's 3 levels. L-1. So if there's 3 levels, there's 2 indicators. Does that make sense? 3 levels, 2 indicators. Yep. And so you just do L-1, which is levels minus 1. So L just stands for how many levels. So there's the levels, 3 levels. So 3 levels minus 1 level. It's always minus 1 because the minus 1 stands for the indicator becomes one that we don't make it for. And what are we trying to say right here? Well, if you just take a look at any model we make, like with handedness, then you make them all for handedness, you summarize it, and you see the 2 indicators right here. You don't see ambidextrous. So it's very clear. Wait, so factors have indicators, correct. A categorical variable, which is called a factor, will create indicators when introduced to a model. So here's the variable added as part of the model. Handedness is being added to the model, and it introduces 2 indicators. So the variable is handedness, and then it introduces or creates 2 indicators. Exactly. Going on. Good questions, everyone. Good questions. Here we go. Next question. Leaderboard: cute lobster, gentle wombat, diligent panda, kind dog, flying panther. Here we go. What do the p-value for the interactions mean? Oof, 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 oof. Let me look at more interaction stuff over here. Interactions. I like this. Nice job. The interactions bring new information. So whenever we have a p-value in a multiple regression model, the p-value tells us if the variables bring new information. So what I've got on the screen right here is AIC tables. They're super duper cool. And usually what somebody does is they make a whole bunch of models and they use the AICs to what their models. So someone makes a whole ton of models and they use the AICs to do what? Ooh, okay, wait. They use the AICs to what? A lot like the questions I'm asking. The exam is really tough. That's why I said I started this by saying the Kahoot's way easier than the exam. Oh, and you're right. AIC is how close our model is to the truth. Or what was the exact, which I don't even use the exact definition. There was something we had it that we saw the exact, and here's the AIC with the penalty term on the end of it. This image is really good here. AICs are how close we are to the truth, and Allison said we're going to use them to compare models. So what you would do right here is you notice they're doing tons of models that they're doing support vector linear, or they're doing with a linear kernel. So they're doing machine learning of sorts. They're doing a support vector machine with a linear kernel. I have no idea what subtype IMAS is. No idea what those are. But they're doing 5 different models. I can tell you that by looking at this. And with their 5 different models, each model gets its own AIC. And this is AICC, which is Akaike's corrected criteria. So what are big differences in AICs? What's a big difference in an AIC? Like, whoa. What's a big difference in an AIC? A big difference in AIC. 10's a big difference. So if you look right here, this is trash. This is garbage. That's kind of garbage. And over here, you get this and you get this. Why do I like those? Doesn't matter, that's support vector linear, support vector machine. Why do I kind of like those? 10 is a big difference. You get this gray zone between 2 and 10. But those are virtually identical AICCs. They're very, very close. And because of that, we would probably use either one of those. If you look, this one is a better standard error. The standard error of the model. Yeah. And those are super close. AIC and AICCs within 2 are virtually identical. So if the AICCs are super close within 2, you could technically use either model. Bigger AIC differences of 10. 10 is a garbage difference. And what is the best possible AICC or AIC? So if you look at how AICC works, it's this right here, and this is going to be the basically error of the model. It's the natural log of the residuals, I believe, it can be done that way. What is the best AICC? What is the best AIC? Anyone know? Negative infinity. Great job, Owen. Negative infinity. Yep, because it just gets lower and 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 lower. So it just goes to negative infinity. You can't get it. The best AIC would have no error. And actually, this is it right here. Look at this. This formula that we just happened across right here with the sums of squared error of the model over the sample size times n. So if your sums of squared is 0, you get log of 0. And if you take the log of 0, it goes to negative infinity. It's a limit. It's an undefined. But the log of, as you approach 0, goes to negative infinity. Just if you don't believe me, log as we go towards negative infinity goes to, it just will keep getting smaller and smaller. So you'll just keep going down. You just can't do log of 0, but I think R will actually say negative infinity. So it approaches the limit of that. Okay. A few more questions. How many more? Here we go. Next question. What does the following show? Oh my gosh. What do we got right here? What is this procedure? What does this show? Who knows? You should know this output. Yep. You will be running this. What is this? Oh no, we only have and 10 people. Good. That is a stepwise procedure, the start of a stepwise selection right there, because you've started at the naive model, you're going towards the complex model with more variables in it, you're going forward, and it's currently at the naive, an AIC of this amount currently, and adding in gender, survey 10, or this is survey 11, is going to be the best choice right here. So if you want to know how to write the step code, please check out the notes on this. Oh my gosh. So we go right here and we make a naive. On the exam, can we use stepwise build model to make a descriptor model? I think you can. If it says do the step procedure, do the step procedure. If it says use the step function, use the step function. Huge suggestion there. So if it says to do that, do that. And know how to write these codes or have examples of it. So here we are with a naive. I like to write my full model the following way. And if we're doing all the variables, we do that. And then my brain has to think, do the step procedure as in step, and we go the naive as the start. And then scope equals list. Scope equals list. And we go here lower equals naive, comma upper equals full, comma direction equals, ooh, I got something going on wrong. Oh, I didn't close my list. There we go, direction, rewrite it. Didn't get the autocomplete, equals forward, and direction equal unexpected. Oh, it's the extra close right here, I think. There we go. And there we go. Here is the step procedure, and the trace is currently on. It's on by default. Trace lets you see the output of it. And you can see the steps it did where it entered in desired weight. It then entered in gender, and you can watch the variables being entered into the model. It then, after entering in gender, entered in weight. It then entered in number of body piercings and kept proceeding till it gave the final model. And then we can even see a summary of the final model right here to see what it made. Do I remove % more attractive then because it's not significant now? Do I remove % more attractive then because it's not significant now? Do I remove percent more attractive because it's not significant? No. If I want this to allow the addition and subtraction of variables, what should the code say right here? Yep. And there you go right there, Evan. Thank you for asking. If I want to do the addition and subtraction of variables, what should the code say right there? If it allows to enter and remove variables. Should be within about 24 hours. Grayson, thank you for asking. If I want to do the addition and subtraction of variables, what should that say? I want the addition and subtraction, both. Allow both directions, and now it can add and subtract, and you see it right there. So both right there. So now the addition and subtraction. Yes. Whew. I've been going since 3. Oh my gosh. Here we go, the leaderboard. Cute lobster, diligent panda, gentle wombat, kind dog, and flying panther. How build model? Yeah, we'll use the build model here with descriptive here in a second. I think use the build model on the test. Little question here, and then we'll do a build model. You got it, Owen. Which way do we interpret height? Now be very careful right here. Be very careful about interpreting coefficients. So very careful. This is for BAS 320. BAS 320. So when we interpret the coefficient right here, why are we interpreting with probability? Why are we interpreting with probability? Why is it in a probability interpretation? So take a look at the output again. And why is it a probability? It's logistic. And when we do logistic, we always interpret the probability of the level of interest. We are always talking about the probability of the level of interest, as in we are predicting in this model if somebody is male. And that is correct right here because we are predicting gender, which is probability. So 2 individuals who differ in their height by 1 inch, the person who is taller is more likely to be male. 2 individuals who differ in their height by 1 inch, the person who is taller is more likely to be male. And so when you think about this, you have to know if it's logistic or if it's quantitative, the linear model, when interpreting your coefficients. And be very careful, because we used to have people write them out, but now we give you multiple choice. And I swear people do worse with multiple choice. Think about this model right here where we're predicting height. So what we have here, 2 individuals who are otherwise identical but differ in their desired weight by 1 pound are expected to differ in their height by 0.1 inches, where the person who wants to weigh more is taller. 2 individuals who differ in their desired weight by 1 pound but are otherwise identical, the individual are expected to differ in their height by 0.1 inches, where the person who wants to weigh more is expected to be taller. 2 individuals who are otherwise identical, but one is male and the other is female, the person who is male is expected to be 1.4 inches taller. Try writing these out, and this is a quantitative model right here. Try writing them out. And let me go do the build model output. You said build model with descriptive. Let's go see that. I'm just going to click that every time. Okay, build model. And let's go right here. We need the form, height, tilde, dot, data equals, and survey. Then its type, is it type equals? Type equals predictive. Predictive. Yes. There we go. What in the world does this mean? So what is this output right here? The very best model has how many variables in it? The very best model has how many variables in it? The very best model has how many variables in it? The very best model has how many? It has 6. So that's where you see the star right here. And then the model that is just as good as it has 2 variables right here. So if you notice right here, oh my gosh, so much output. The 2 variable model with gender and desired weight is just as good as a model with 6 variables in it. Now, how do we pick our model? Do we pick it on the generalization error or the estimated generalization error? Which of those is how we pick our model? Do we pick our model on the estimated generalization error? And the answer is on the screen. Or the generalization error? How do we pick our model? How do we pick our model? The estimated generalization error is how we pick our model. So we pick it on the estimated generalization error because that's how we think it will do. We think it'll do as well as the estimated, and then we see if the estimated generalization error is as close as it is to the actual generalization error. So we pick it on the estimated generalization error. So this would suggest using a model with 2 variables in it, and it even shows the coefficients right there of the model that is just as good as it. And the best model is the 6-variable model, which has a lot more stuff in it than we probably need. And looking at here, we're doing it on the k-fold cross-validation process to see how we would estimate the models would do. Really good question, Owen. I hope that helps out. Let me know if it doesn't, but that's how we pick it on the predictive model right there. You can use type equals predictive and also make descriptive. So a good predictive model and a good descriptive model are generally like, if you have a good predictive, it's generally a good descriptive. They kind of work hand in hand, but descriptive models are gauged on AIC because it's closer to the truth. Predictive models are gauged on how they work on new data, with generalization error and estimated generalization error being how we pick it. So predictive models are picked on estimated generalization error. Descriptive models are picked on AIC. How do we get the estimated generalization error to pick the model? It's done for you. It's done via the k-fold cross-validation process. The k-fold cross-validation process is when we take our data and chop it into 5 parts. So you take your data right here, and you can do 4 parts, k-fold 4. And then you go here with validation, 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 and then this becomes the training, whoops, wrong. Training, 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 and this is validation. And then you do the process iteratively where you move the validation portion to the next fold and you make the models. So this estimate you're seeing right there is created from doing this process 4 times, creating an estimate of how the model will do when the training portions make the data, and then the validation portion is used to see how it works on that new data it hasn't seen. It's called a pseudo holdout because the model actually uses that data throughout the 4 folds, just 3 of the 4 folds don't use it. Good question. Leaderboard, cute lobster, diligent panda, gentle wombat, kind dog, and fearless newt. Here we go. Which of the following is true about r squared adjusted? The r squared adjusted has what true about it? What is true about it? Adjusted r squared. Question. In a very in-depth review. So with this right here, r squared adjusted exactly everything, but it can't be over 1. It can't be over 1. That is true. And when we think about this right here, it's a penalized r squared. It can be negative, and we definitely use it to compare models. Huge right there. Very important things. And when we think about the sigmoidal curve, the sigmoidal curve looks like a what? The sigmoidal curve looks like a what? What does the sigmoidal curve look like? What does the sigmoidal curve look like? What does the sigmoidal curve look like? It looks like an S. Sigmoidal curve look like? The sigmoidal curve looks like an S. Sigmoidal curve looks like an S. And it's bound by what and what? What is the sigmoidal curve bound by? The sigmoidal curve is bound by what and what? 0 and 1. Very important right here. Bound by 0 and 1 is probabilities. The sigmoidal curve is bound by 0 and 1. Really good stuff right there. Sure. Be able to get these. I hope. Sigmoidal curve, we should know this stuff. I hope we do. But it's a tough test. Tough test. Okay, next question. Here we go. Just a few more. Leaderboard, cute lobster, diligent panda, gentle wombat, fearless newt, and kind dog. Someone creates regression using months of the year. How many indicators? Great review question. how many indicator variables will there be? How many indicators with months of the year? So you have to know how many months of the year there'll be. How many indicator variables would there be? Months of the year. Like this. So, yes, 11. Good work on that. It's levels -1. So, one thing to note is when we do our models, especially when we do predictive modeling, we basically have the estimated generalization error and we have the actual generalization error. So they generally increase with each other. And the model that works the best would be where? I think Owen answered this one. Where's the model that works the best? The model that works the best would be where? Where's the model that works the best? Where is the model that works the best? Where is it on this graph? Where's the model that works the best? Ah, oh, it is, isn't it? Oh man, you're right. It is this model because it has the lowest generalization error. But here's the thing. We would have picked this model because we estimated it would do the best. So that means all the models here, will technically here over, do better than our model. So when we do the estimate, we usually get a good model, but we're not insured to get the best model. There's tons of models that could be better than our model, and we don't know it because, and here's the thing, what I asked when I was a student, I was like, well, why don't we just pick, you think, well, if this model over here works the best, why don't you just pick this data, or that model, excuse me. Why don't you just pick this model if it works the best on new data? The point of this procedure is not to just pick a model that works the best. It's to say, here's how I think the model will work, and then here's how the model actually works. You never end up making this graphic that I drew right here because you never end up testing all your data on the holdout. You only make one model and test it on the holdout to see if it works, and if it works, you use that model. And you pick the model you think will work the best, and then if it works good enough, then you use it. You don't pick the model based on how it works on the holdout, or you're just fitting to a holdout then. Does that make sense? I think that kind of blew my mind when I realized it, like, wait a minute, if we just pick the one that works on the holdout, we would literally just be fitting to the holdout. So that is something we don't do. We don't just fit to the holdout. We fit our model to the data and do a pseudo cross-validation holdout on it to see how it'll work. Here we go. Dude, lobster, diligent panda, gentle wombat, fearless newt, kind dog. Next question. Which order should we use? Classic review question right now. Do you know the order we should use? Do you know? Which order should we use? This one is a bit tricky. Good review question. You can't use the AIC trick for it. Order 2? Did I get this right? Hopefully I got it right. Yeah, I think it is. Wait a minute. It's super close. Technically, I think I'm wrong on this, aren't I? Take a look. Technically, it should be order what? It's super duper close, but since I didn't include it, does anyone want to correct this? Because technically, I think I'm wrong. Technically, it's going to be what? It's super duper close to that, but that's what I thought. What I was doing. Yeah, technically 4. So sorry if anyone got that one wrong right there. Technically it's 4. But this is super crazy close. Technically on the test, you put 4. So hopefully no one lost their streak on that. You can see someone losing their streak. But technically it would be 4. You could go with 2 though, because it's super duper close. Be like, well, it's really close to that. And the output kind of shows it. It really levels off around 2. And do not go by AIC. Do not go by AIC. Don't do that on the test. Use the procedure, and we just did it right there. Do not go by AIC. Lobster, cute lobster, diligent panda, gentle wombat, fearless nude, and kind dog. Next question. Which value tells us the model is statistically significant? Looping back to where we started. Which value tells us the model is statistically significant? Brings with it information that is important and relevant. Ooh. I am gonna go get some food, maybe get some sleep. We've been going to bed at like 8:30 at night. Food and sleep. And thank you everyone for being here. Did people learn a lot? We did a lot of output here, and definitely go through the review slides, make your notes. The test is tough. Very wordy, big test. You have to know what you're doing. A tough test. I cannot understate it enough that it's a tough test. I'm hoping very competitive. I want us to have as good a grades as Petrie or higher. All right, Petrie, I want. These are a hard class. How will this exam compare to the midterm? About the same difficulty. They're tough tests. Show another Logit question. Yeah, I'll do a Logit one here. So Logit would always come from. Let's announce the winners right here. Wow, everyone got the p-value. I like that. The winners are cute lobster, diligent panda, and gentle wombat. So we don't do a lot. Logit. Logit's not even mentioned, as far as I can see. Logit would always come from a logistic regression, but when you're doing predictions from a logistic, you always want type equals response. So make sure if you're doing predictions from a logistic, you need to have type equals response right here. So does that make sense? Best way to say, yeah, I would totally do that. Since considering we can use, yeah, I'd go through literally what Petrie put on it, and I'd look through everything Petrie has written that is going to be on it and start making notes. I'll also do one more example of how to do a step function. Yep. So, well, I don't think we asked the logit anywhere on there, but the logit is what you get if you don't do type equals response. And the step function, you need to build your naive, and the naive is going to be ~1, and you have to build the full. You know the average for the finals are, they're usually in the 70s. So you have to build a full and a naive. And then you go through here and you do save into step, naive, scope equals list, lower equals naive, upper equals full, comma, direction, and then depending on which direction you want to go. There you go. Will you have to write a step function or just interpret the output? You might have to write it. You might have to write it. Know how to write it. Know how to write anything I've written right here. Know what the codes are doing. Know how to read them. Create a naive model right here. There's the naive. Create the full model with all the variables. Step function reads. Start with the naive. The scope of models to check. Go from the lower of the naive to the upper of the full. So right there. Good stuff. Keep reviewing. Let me know if you have questions. Post them on the Discord. With that, I'm going to head off. I'm almost on hour number 4. So with that, we'll do a Star Wars outro. Bye for now, everyone. Bye. 5 hours. We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.